6 millibars. That is the entire atmosphere of Mars. Less than 1% of the pressure holding the glass steady in your window tonight. Stand on that surface without a suit, and the moisture on your tongue and your eyes would begin to boil at body temperature. Not from heat, but from the absence of anything pressing back. We have sent more than 50 missions to Mars. NASA has said publicly, more than once, that roughly half of them failed, and in 70 years of serious planning, the hardest problem has never really been the rocket. Tonight, we are going to walk through the plan to live there slowly, the way a surveyor walks through a house before anyone signs anything. Not to talk you out of the dream, only to show you where the floor is not finished yet. Some of what we find has been measured to the decimal. Some of it has never been tested by anyone, anywhere. That second list is the frightening one. Nothing here needs remembering. Let the room stay dark, and let us go and look. Before we go anywhere, let the room settle around you. Whatever position you are in is the right one. If the light is already off, leave it off. If the phone is lying face down beside you, and this is only a voice in the dark, that is exactly how this was meant to be heard. There is nothing to follow tonight, and no moment later on where you will need to have been paying attention. I want to be careful with you from the first minute, because this subject has a bad habit of being handled carelessly. There is a kind of video about Mars that gets made a great deal. It is loud. It tells you that everything you were promised is a lie, that the whole idea is doomed, that the people working on it are fools. And there is another kind, just as common, that goes the opposite way. It shows you a green valley with a river in it and a blue sky that has never existed, and lets you believe the only thing between us and that picture is money and patience. Tonight is neither. Tonight is a survey. Think of what happens before someone buys an old house. Not the tour, where the owner shows you the light coming through the kitchen in the afternoon. The other visit, the quiet one, on a weekday, with a person who has no feelings about the house at all. They walk the room slowly. They tap the walls. They look under things. They are not there to talk anyone out of buying. They are there so that when the signature happens, it happens with the whole picture in the room. That is the walk we are taking. Mars is the house. And I should tell you now, so it is settled and you can stop wondering, that I like this house very much. Nothing tonight is an accusation. It is an inventory. Your shoulders can come down from wherever they have been sitting all day. Now the word in the title, because I put it there, and I owe you an account of it. Terrifying. When most people hear that word attached to space, they think of a sudden thing, an impact, a radiation burst, something arriving out of the dark that we did not see coming. That is not what tonight is about. And if that is the fear you came for, you can let it go now and rest easier for it. The kind of fear this subject contains is quieter and stranger, and it takes a moment to explain. It is the fear of the blank space. Imagine a survey report on that old house, page after page of measurements. The beams are this thick. The roof was replaced in a certain year. The wiring meets a certain standard. Line after line of solid, checkable fact. And then, somewhere in the middle, one line reads differently from all the others. It says that nobody has ever checked the foundation, not that the foundation is bad, not that it is good, that in the entire history of the building, no one has ever once looked. Everything else on the page is information. That one line is something else. And the strange thing about a line like that is that it does not get easier the longer you look at it. It gets worse. Because you begin to notice how much of the rest of the report is resting on top of it. Mars has several lines like that. Not many, but the ones it has are load-bearing. So here is the agreement I want to make before we take a step further. Everything in this house falls into one of three categories. And I am going to keep telling you which one we are standing in. Some things are measured. Instruments were sent. Readings were taken. Papers were published and argued over and confirmed. When we are on that ground, I will name the mission and the year and the people who did the work. So that, if you ever want to check me, you can. Some things are debated. Real scientists, looking at the same evidence, arriving at different answers. That is not weaker ground. It is younger. When we are there, I will tell you where the disagreement runs and who is standing on each side of it. And some things have never been tested by anyone. Not tested and failed. Not tested and passed. Never attempted. By an experiment. On any world. In the entire history of our species. There are fewer of these than you would expect. And more of them than almost anyone realizes. That third category is what tonight is really about. And I will always tell you plainly when we have arrived at one. I will not blur it. I will not let a beautiful sentence carry you across the line from what we know into what we hope, which is the easiest mistake in this whole subject, and the one I most want to avoid making to you while you are half asleep and trusting me. That is the whole promise. It is small, and I intend to keep it exactly. One more thing about the title before we begin. It says, The Terrifying Problem, singular, one problem, and you are about to hear about a great many problems. So I want to be straight with you about how that resolves. Everything we walk through in the first several hours is real. Radiation, landing mass, perchlorate in the soil, sealed air. Every one is a genuine obstacle that serious people are genuinely working on. But none of them is the one I mean. The problem in the title will not become visible until the rooms have been inspected together. It only appears once everything else is laid out side by side, which is why it takes all night to reach. We will name it directly and slowly. Near the end, you do not have to stay awake for it. It will still be named whether or not you hear it. And the walk itself is worth taking either way. Let me give you one last thing before we start, because it changes how the whole evening feels. This plan is old. Picture a room in Huntsville, Alabama, in the early 1950s. A drafting table, a slide rule, sheets of paper covered in orbital mathematics worked out entirely by hand. There is no computer in the building that could help with this. The man at the table has spent months on trajectories for a journey nobody has any means of making. His name was Wernher von Braun, and in 1952 he published the result as a book called Das Mars Project, which in English became the Mars Project. In it, he laid out a full expedition, a fleet of 10 ships, 70 people, departure windows, fuel budgets, arrival geometry, all of it computed on paper. Sit with the date, 1952. No human being had been to space. Not one. Yuri Gagarin would not leave the ground for another 9 years. Sputnik had not flown. The transistor was barely 5 years old. There were no satellites in the sky above the man doing those calculations. No photographs of Earth from orbit. No confirmation that a person could survive weightlessness for even an hour. And already, on paper, in a room in Alabama, someone had written down the fuel needed to move 70 people to another planet and bring them home. That is how long this has been sitting in the human imagination as a solved problem waiting for a budget. 70-odd years later, a great deal of that arithmetic has held up beautifully. The orbital mechanics were right. The trajectories were right. What von Braun could not have known, because nobody could have known it yet, is what the hard part would turn out to be. That is the house we are about to walk through. You do not need to hold on to any of this. Not the year. Not the name. Not the number of ships. All of it will still be true in the morning, whether or not any of it stays with you tonight. A surveyor always begins in the same place. Not with the roof, and not with the rooms, with the road in. Here is something that almost never makes it into the way we talk about going to Mars. You cannot leave whenever you want. We are so used to the idea that travel is available. There is a road, and the road is always there. And you go when you are ready. Even the extraordinary journeys work this way. A ship to Antarctica leaves on a schedule someone chose. A flight across an ocean departs because a person at a desk decided it should. The world runs on the quiet assumption that departure is a matter of will. Mars does not work like that at all. Mars has a door, and the door is on a timer. And the timer belongs to the solar system rather than to us. Both worlds are moving. Earth goes around the sun once every 365 days, which is the entire reason we have a year. Mars, being farther out, has a longer way to travel and moves more slowly along its path. It takes about 687 Earth days to complete one circuit, nearly 2 of our years for one of theirs. So the two planets are not sitting at fixed addresses. They are two runners on two concentric tracks, moving at different speeds, constantly changing position relative to one another. Sometimes they are on the same side of the sun. Sometimes they are on opposite sides, with the sun itself standing in the gap. The distance between Earth and Mars is never one number. It is a number that breathes, in and out, across a cycle taking a little over 2 years to repeat. At closest approach, the two worlds come within roughly 55 million kilometers. At the far side of the cycle, that gap opens to something over 400 million, the same two planets, the same orbits, a distance that changes by a factor of 7, depending on when you happen to ask. There is nothing in this that needs solving. It is simply the arrangement. Now, the natural thought is that you wait for the two planets to be closest and then go. That is the intuitive answer. And it is wrong. And understanding why is the most useful thing in this chapter. You are not aiming at where Mars is. You are aiming at where Mars is going to be. A spacecraft leaving Earth does not fly the whole distance under continuous power. Rockets work by throwing mass out the back, and every gram of that mass has to be carried from the beginning. So the fuel budget allows only a small number of burns. What actually happens is closer to a very long throw. You fire the engines for a matter of minutes near Earth, and then almost everything after that is coasting, following a curved path determined by gravity, with a handful of carefully planned correction burns along the way to keep the aim true. That path has to be arranged so the spacecraft and the planet arrive at the same piece of empty space at the same moment, after a journey lasting most of a year. This is why the transfer window exists. There is a specific arrangement of the two planets, a particular geometry, that allows a spacecraft to leave Earth on a curve and meet Mars at the far end without spending an impossible amount of fuel. When that geometry arrives, you can go. When it passes, you cannot, no matter how ready you are. The most efficient version of this path was worked out by a German engineer named Walter Hohmann, and he published it in 1925. Sit with that year. The mathematics governing when a spacecraft may depart for Mars was written down 32 years before anything at all had been placed in orbit around the Earth. The transfer orbit still carries his name. The geometry lines up roughly once every 26 months. That is the number. About 2 years and 2 months. And once you know it is there, you begin to see it in the history of the missions. 1996. Then 1998, 2001. Then 2003, 2005, 2007, 2011, 2013, 2018, 2020. The launches come in clusters, and the clusters come in pairs of years. And between them, nothing goes at all, because nothing can. There is a version of this that is almost beautiful. Every 26 months, the various space agencies of the Earth, which do not always agree about very much, all find themselves working toward the same handful of weeks. Rockets in Florida and in Kazakhstan and in French Guiana and in Hainan, all pointing at the same window. And then the window closes. And there is silence on that road for 2 more years. And nobody on this planet can do anything about it. Here is where it becomes a real constraint on human life. The trip itself, on that efficient curve, takes somewhere in the region of 6 to 9 months. Different mission plans give different numbers depending on the trajectory and the year. But that is the honest range. And it is not a range anyone chose. It falls out of the physics. So imagine you go. You spend 7 months crossing. You arrive. You cannot come back. Not because anything has failed, because the door on the other side is on the same timer. When you arrive at Mars, Earth has moved on along its own faster track, and the geometry for the return journey does not exist yet. You have to wait for the 2 planets to come back around into the right arrangement. Depending on the mission design, that wait is somewhere between about 30 days and about 500 days on the surface. The short version, the one where you stay a month, sounds appealing until you learn the cost, which is a much faster and more punishing trajectory in both directions, and a great deal more fuel. The long version, the one most serious study groups favor, means you land and live there for something near a year and a half before the road home reopens. Add it up, 7 months out. Something like 500 days there. 7 months back. A round trip occupying roughly 2.5 to 3 years of a human life. And almost none of that duration is a choice anyone made. It is the shape the solar system imposes. Now, the consequence. And it is one of the most human things in this whole survey. Every great expedition in human history has had a possibility folded inside it, even when it was never used. The possibility of turning around, not the guarantee. Nobody is claiming that Shackleton or Amundsen or the crews of the old sailing ships had any real safety. Plenty of them never came home. but the direction of return existed. It was a thing you could point at. If a ship in the Southern Ocean lost half its crew to illness, the captain could give an order and the ship could come about. And whether or not they survived the attempt. The attempt was available. There is a version of this in space too. In April of 1970, when an oxygen tank ruptured aboard Apollo 13 on the way to the moon, the crew survived by looping around the moon and coming home on what is called a free return trajectory. Gravity itself brought them back. The road was still there, running in both directions, 3 days wide. I want to be precise about the Mars version because it is easy to overstate. There is no Apollo-style return that brings you home within days. Some mission architectures do include long, free return or abort trajectories, and orbital designers have studied them seriously. So it is not true that turning around is mathematically forbidden. What is true is that those options are slow. They are not available from every point in the journey, and none of them amounts to simply coming about. A free return that takes 2 years to deliver you home is not a rescue in any sense a sick person would recognize. So the honest version is this. If something goes wrong 4 months into the crossing, the vehicle is on a curve that was chosen a year in advance, and the realistic options are measured in months and years rather than in days. The only useful door is the one at the far end. This is the first line in the survey report, and it is one of the most certain things in the whole building. The orbital periods, the transfer windows, the 2-year rhythm, the duration of the crossing, the weight on the surface. This is Newtonian mechanics of the sort that has been checked by every successful mission ever flown to that planet. And it has never once been wrong, which is a strange kind of comfort. The first hard thing about Mars is also the most certain thing about it. There is no ambiguity here at all. Notice what that does to the emotional weight. A known constraint is a very different object from an unknown risk. You can plan around a locked door if you know precisely when it opens. And every mission architecture ever seriously proposed has done exactly that. Building that rhythm into supply schedules, crew rotations, and the timing of cargo sent ahead. So this is not the terrifying part. This is the part where the universe states its terms clearly and in advance, and lets us prepare. Hold on to the shape of that, if you hold on to anything. Tonight we are going to meet several problems where we do not have this luxury at all. We now have a road, a departure date, and a passage of 6 to 9 months during which the vehicle mostly coasts through empty space toward a moving target, which brings us to what is quietly passing through that vehicle from outside, in every direction, without ever slowing down. There is a measurement I want to give you tonight, and I want to build up to it properly, because a number handed over without context is just a sound. We are going to talk about radiation. Stay with me, because this is not the part you are expecting, and the truth of it is more interesting than the version that usually gets told. Start with where you are. Right now, lying in that room, you are being protected by 2 things you have never once thought about, and both of them are enormous. The first is the atmosphere over your head, not just the air in the room, the whole column of it, running from your roof to the edge of space. 60-odd miles of gas stacked above you. That column has real mass. Every square meter of ground on this planet is carrying somewhere in the region of 10,000 kilograms of air on top of it, which is roughly the equivalent of standing beneath 10 meters of water, or beneath several meters of ordinary concrete. Everywhere, all the time. It has been there your entire life. You have never noticed it once. The second is a magnetic field, generated by the planet itself. Deep down, beneath the mantle, there is an outer core of liquid iron and nickel in constant convective motion, and that moving conductive metal generates a magnetic field extending far out into space in every direction. It is the reason a compass needle points north. It is also, and much more importantly, the reason charged particles arriving from the sun get deflected around this planet instead of into it. Two shields, one made of air, one made of a spinning iron heart. Neither of them chosen, neither designed, both simply here, doing this work above every sleeping person on Earth for as long as there have been sleeping people. Both of them are still working right now. Now, step outside all of that, out beyond the magnetic field. In the space between the planets, two quite different things are arriving. The first comes from our own sun. These are solar energetic particles, associated with flares and with the large eruptions of material called coronal mass ejections. The sun is not steady. It has an 11-year cycle of activity, and during the busy parts of that cycle, it periodically throws out enormous quantities of high-energy protons. The important thing about this first type is that it is dramatic but manageable. A solar particle event is a storm, and storms arrive and pass. Because the particles involved are relatively low in energy, though not low by any human standard, a sufficiently thick shelter actually works. Most serious spacecraft designs include what is called a storm shelter, often just a small volume in the middle of the ship, walled in by things you were carrying anyway. Water tanks, food supplies, waste, anything with mass. The crew moves in, waits out the event, and comes out again. That is a solvable problem. Uncomfortable, expensive, but solvable, and it is well understood. The second thing arriving is the one that matters, and it is much stranger. These are galactic cosmic rays. They do not come from the sun, they come from outside the solar system entirely, and the leading explanation is that they are accelerated by the shock waves of supernovae, the deaths of stars in other parts of the Milky Way, some of them very far away and very long ago. They are atomic nuclei, stripped bare of their electrons, moving at a substantial fraction of the speed of light, mostly hydrogen, a good deal of helium, and a small but significant fraction consisting of much heavier nuclei, iron among them. Here is the thing about them that changes the whole picture. They never stop. There is no burst, no event, no storm to wait out. Galactic cosmic rays are a constant. Faint rain falling through the entire solar system at all times, in every direction, and they have been doing so since long before the sun existed. You do not shelter from them for an afternoon. They are simply the condition of being outside a planet's protection. Before I give you the number, I want to give you the reason I trust it. In November of 2011, NASA launched the Mars Science Laboratory, carrying the rover we know as Curiosity, bolted inside the cruise stage, positioned in a way that roughly approximated where a human being would sit, was an instrument called the Radiation Assessment Detector, and during the entire cruise to Mars, it was switched on. That is the detail I find quietly wonderful. On the way to deliver a rover, we ran the experiment, not a simulation, not a model, an actual instrument, actually crossing the actual distance, taking readings for the actual duration of the journey, sitting behind a realistic amount of spacecraft structure, 253 days, 560 million kilometers, listening the entire way. The results were published in the journal Science at the end of May 2013, with Carrie Zeitlin of the Southwest Research Institute as lead author, alongside colleagues including Donald Hassler, who led the instrument team. Here is what they found. The average galactic cosmic ray dose equivalent rate during cruise was about 1.8 millisieverts per day. Extrapolated to even the shortest realistic round trip with current propulsion and comparable shielding, the total came out at 0.66 sievert, with an uncertainty of 0.12, 660 millisieverts. Then, for the transit alone, not including a single day spent on the surface. Now, I have to translate that, because millisieverts mean nothing to most of us. Natural background radiation on Earth, from radon in buildings and cosmic rays that make it through the atmosphere, and radioactive potassium in your own body, averages somewhere around 2 to 3 millisieverts a year, depending on where you live. Add medical imaging, and the total in a country like the United States roughly doubles. But the natural component is the useful comparison here, because nobody is choosing it. A chest X-ray is about 0.1 millisieverts. A full-body CT scan is somewhere in the region of 10. Zeitlin's own comparison was that the accumulated dose during cruise amounts to something like a whole-body CT scan once every 5 or 6 days. Let me be extremely careful here, because this is precisely the point where these videos usually go wrong. That dose does not kill you. It is nowhere near an acutely lethal exposure. Nobody arrives at Mars sick from this. The people who did the research have been consistent and clear on that point. What it does is raise a lifetime probability. The main concern is an increase in the risk of developing a fatal cancer later in life, and the estimates carry real uncertainty. It is a statistical shadow rather than an event. That is a very different thing from a poison, and I want you to hold the difference clearly. Now, the part that is genuinely counterintuitive. You cannot simply add shielding. Everyone's instinct is to build a thicker wall. More metal, more mass, more protection. That is how shielding works for almost everything else. And it is broadly true for the solar particles we discussed a moment ago. For galactic cosmic rays, it can make things worse. When one of those heavy, extremely fast nuclei strikes the aluminum hull of a spacecraft, it does not politely stop. It smashes into a nucleus in the wall and shatters it. And the collision produces a spray of new particles heading onward into the interior. Neutrons, protons, fragments of the broken nucleus. A whole secondary cascade generated by the wall itself. This is called secondary radiation, and the effect is that a moderate thickness of the wrong material can turn one incoming particle into a shower of several, which then arrive at the crew. The shield becomes a source. Zeitlin put it plainly when the results came out. Even an aluminum hull, a foot thick, would not change the dose very much. Read that again, gently, because it is one of the most elegant and infuriating facts in this entire subject. There are answers being worked on. Hydrogen-rich materials perform much better, because a hydrogen nucleus is a single proton with no larger structure to shatter into fragments. This is why water and polyethylene keep appearing in these designs, and why one recurring proposal is to build the shelter walls out of the water and food and waste the mission has to carry regardless. Active magnetic shielding has been studied for decades, essentially generating a small artificial magnetosphere around the vehicle, and it remains an area of genuine research rather than an available solution. But there is no version where you wrap the ship in metal and the problem goes away. The physics does not allow it. So, where does this sit? The dose is measured. We flew the instrument. Zeitlin and Hassler and their colleagues published the readings, and anyone can look them up. This is one of the best characterized hazards in the entire survey, and we have known the number for over a decade. The consequence of that dose is where the disagreement lives. And honestly so. Our entire understanding of radiation risk in humans is built on populations exposed to something quite different. Survivors of the atomic bombings, medical patients, nuclear industry workers. Those exposures were mostly gamma rays and X-rays, delivered in different patterns, and the biological damage caused by a fast iron nucleus tearing through tissue is not the same kind of damage at all. Estimates of the added lifetime cancer risk exist. They are taken seriously, and the people who produce them will tell you frankly that the error bars are wide. The word for that is uncertainty, not danger. They are not the same thing. And one of the quiet gifts of a night like this is having the time to keep them separate. And now, the last piece, which reframes the whole chapter. Everything discussed so far applies to the journey. 6 to 9 months out, 6 to 9 months back. But the door on the far side does not reopen immediately. The realistic mission profile has people on the surface for something like 500 days. The same team ran the numbers on that too. Once the instrument had been sitting on Mars long enough to speak, a 500-day surface stay, added to the transit, brings the total to somewhere in the vicinity of 1 sievert. That figure is worth noting, and worth stating carefully. A mission total near 1 sievert sits in the range that several agencies have historically treated as a career-level exposure for an astronaut, meaning the accumulation of an entire working life. Those limits are not a single fixed number handed down from somewhere. They differ between agencies. They have been revised as the underlying risk models improved. And modern approaches consider individual factors rather than applying one ceiling to everyone. But the shape of it stands. 1 mission, something close to a career. We will get to what daily life looks like under that constraint, and to the rather claustrophobic conclusion that many settlement designs have independently arrived at. But before anyone can live on the surface, there is a smaller and more immediate problem, and it has already destroyed a remarkable number of missions. Getting down there in one piece. Let me set a scene, and then take it apart. A room somewhere in Southern California, rows of people at consoles. Most of them young, all of them very quiet. Somewhere in the middle of that room, a clock is counting, and every single person there knows that whatever is about to happen has, in a strict sense, already happened. That is the strange arithmetic of arriving at Mars. Radio signals travel at the speed of light, which is the fastest anything can travel, and it is still not fast enough for this. Depending on where the two planets are in their long cycle, a message from Mars takes somewhere between about 4 and about 22 minutes to reach us. Around the time of a typical landing, the figure is often somewhere in the region of a dozen minutes, though it varies with the year. The descent takes about 7 minutes. So the signal announcing that the spacecraft has entered the atmosphere is already old when it arrives. By the time those words reach the room in California, the vehicle on Mars has either been sitting safely on the surface for several minutes, or it has been scattered across it for several minutes. The outcome is settled. The news is simply still in transit. Nobody in that room can do anything. There are no controls. There is no override. Everything that will happen was written into the software months earlier and loaded aboard, and the machine has to fly the entire sequence by itself, on a world nobody in the room has ever been to, using only its own senses and its own judgment, while the people who built it sit in the dark and wait for the past to arrive. This is what they mean when they say, the 7 minutes of terror. Let the clock in that room finish counting without you. This one has already ended. Many times. And mostly well. Now let me explain why those 7 minutes are so hard. Because the reason is genuinely surprising, and it comes straight back to the number we opened with. 6 millibars. There are 2 ways to slow something down when it arrives at a planet. And Mars has arranged itself so that neither one works properly. The first way is atmosphere. You come in fast. You hit gas. The gas resists. And the friction bleeds off your speed. This is how everything returning to Earth is slowed. A capsule coming back from orbit is traveling at something like 28,000 kilometers per hour, and by the time it is a few kilometers up, the air alone has done nearly all the work of stopping it. Parachutes handle the gentle remainder. It is a spectacularly effective system, and it is free, in the sense that you do not have to carry it. The second way is engines. No atmosphere at all, as at the Moon, and you point rockets downward and burn against gravity until you touch. Also effective, not free, because every second of that burn has to be paid for in propellant carried across space. Mars sits precisely in the gap between those two solutions, and it gets the worst of both. The atmosphere is thick enough to matter. It is not nothing when you are moving at 20,000 kilometers per hour. It will heat your vehicle to thousands of degrees. It will require a full heat shield. With all the mass that implies, you must survive it. And then, having paid the entire cost of an atmospheric entry, you find the same atmosphere is far too thin to actually stop you. The comparison people use, and it is a fair one, is that the surface pressure on Mars is roughly what you would find about 30 kilometers above the Earth. That is 3 times the altitude of a passenger aircraft. Parachutes barely function up there. And on Mars. That is not the upper atmosphere. That is the ground. So you carry the heat shield, and you take the punishment of entry. And at the end of it, you are still moving far too fast. And now you need engines as well. Both systems. Full price for each. This is why the Mars landing record looks the way it does. There is a long and sobering list of spacecraft that arrived successfully and then did not survive the last few minutes. The Soviet Mars 2 lander in 1971, Mars 3, which touched down and transmitted for about 20 seconds before falling silent. NASA lost Mars Polar Lander in 1999. Europe's Beagle 2 reached the surface in 2003 and was later found in images to have landed but never fully unfolded. The Schiaparelli demonstrator. part of the ExoMars program, was lost during descent in 2016. These were not careless projects. They were built by extremely capable people who understood the physics completely. That planet is simply arranged so that arrival is the hard part. You do not need to remember a single one of those names. Let them go past like stations seen from a train. And now we come to the part that actually matters for our survey. Because everything so far has been about machines. And machines are small. Here is the constraint. The heaviest object human beings have ever successfully placed on the surface of Mars is the Perseverance rover, which landed in Jezero crater in February of 2021. It weighs about 1,025 kilograms. Curiosity, its predecessor, is close to 900, 1 metric ton. That is the record. That is the top of the mountain. Now let us ask what a crewed landing would need to weigh. Study groups at NASA and elsewhere have worked this out repeatedly. And, while exact figures vary between architectures, the range that keeps appearing in the literature is somewhere in the region of 20 to 40 tons for a single crewed lander. Not the whole mission. Not the supplies for a settlement. One vehicle, containing people, capable of setting them down alive. 20 to 40 tons, against a demonstrated record of 1. I want to be careful how I say this next part, because it would be easy to make it sound like an accusation. And it is not one. That is not an incremental step. Everything about entry, descent, and landing scales badly. A heavier vehicle carries more energy into the atmosphere and needs to shed more of it. Parachutes do not simply get bigger, because at supersonic speeds in a thin atmosphere, the fabric behaves in ways that become unstable and unpredictable. And there is a real ceiling on how large a supersonic parachute can usefully be. NASA spent years testing exactly this problem with a program called the Low Density Supersonic Decelerator, flying large inflatable and parachute systems in the upper atmosphere over Hawaii in the mid-2010s. And some of those tests tore themselves apart. The leading approaches to closing this gap are real and are being worked on. Inflatable heat shields, which pack small and deploy into something much wider than the rocket that carried them, have been flight tested. NASA flew a demonstration called Lofted in November of 2022, and it survived re-entry at Earth. Supersonic retropropulsion, meaning firing rocket engines forward into the oncoming airflow while still moving faster than sound, is the other major approach. And it is the one most large vehicle concepts depend on. So this chapter is a genuinely mixed case, and the honest answer is more interesting than a simple verdict. The physics is measured, the atmospheric density, the entry velocities, the heating, the limits of parachutes at those speeds, all well characterized, confirmed by every vehicle that has made the attempt, successful or otherwise. The 1-ton record is simply a fact of the historical record. The path to 20 or 40 tons is where the argument lives. And here I want to be scrupulous. There is no law of physics standing in the way. Nobody serious claims it is impossible. There are credible engineering routes, and some of the hardware has already flown in test form. What there is not, as of the time this was written, is a demonstrated landing of anything approaching that mass on that particular world. Notice how different this feels from the last chapter. Radiation is a problem where we know the number precisely and are uncertain about what it means. Landing is the opposite. We know exactly what it means, and we are uncertain whether we can do it yet. Two obstacles. Uncertain, in completely different directions. I find that oddly comforting, and I want to tell you why. An engineering gap is the friendliest kind of obstacle there is. It has a shape. You can measure the distance to it. You can build test articles and fly them, and watch them fail and build better ones. Every one of those Mars landing failures produced data that made the next attempt more likely to work, which is why the recent record is so much better than the early one. This is a problem that responds to effort. So set the landing down now. Let it be solved, in your imagination, by whatever combination of inflatable shields and forward-firing engines eventually manages it. Let the vehicle be intact, and the dust be settling, and the crew be alive, because the moment they are down safely, a different set of questions begins, and they begin with the one thing that is genuinely, permanently wrong with that place: the air. There is a mistake almost everyone makes about Mars, and I made it too, for years. The mistake is thinking of Mars as a cold desert. It is an understandable picture. The images that come back look like desert. Red-brown ground, scattered rocks, dewness, a sky with weather in it. There are dust storms. There are clouds, thin and high, made of water, ice, and carbon dioxide. There are seasons, and frost in the mornings at high latitudes. It looks like a place. It looks like somewhere in Utah or the Atacama, with the color turned up and the temperature turned down. That picture is wrong in a way that matters enormously. Mars is not a cold version of Earth. Mars is a slightly softened version of space. Start with composition, because it is the easiest part. The atmosphere of Mars is roughly 95% carbon dioxide, with small amounts of nitrogen and argon and traces of other things. Oxygen makes up something like 0.1%. This has been measured directly, from orbit and from the surface, most precisely by the sample analysis instruments aboard Curiosity. So the air is unbreathable. That much everybody knows. And it is where people usually stop. Fine. You bring oxygen. We have done that for divers and submariners and astronauts for decades. But composition is not the real issue. The real issue is quantity. 6 millibars. On Earth. At sea level. Atmospheric pressure is about 1,013 millibars. That is the number your body was designed around. And it has been pressing evenly on every square centimeter of you since the moment you were born. You have never felt it. It is like asking a fish about water. Mars runs at about 6. Not 6%. 6 against 1,013. Less than 1% of what is holding your body in its ordinary shape tonight. Now what that actually means, and I am going to be precise rather than lurid, because this is a fact that gets exaggerated constantly, and the truth is remarkable enough without help. There is a threshold in the human body called the Armstrong limit, named after Harry Armstrong, an American Air Force physician who identified it in the 1940s. It sits at roughly 63 millibars. Below that threshold, water at normal human body temperature will boil. Read that again slowly. Not hot water. Water at 37 degrees Celsius. The temperature of the inside of your mouth right now. Boiling is not really about heat. It is about the relationship between temperature and pressure. Water boils when the pressure around it drops low enough that the molecules can escape into vapor. On a mountaintop, where pressure is lower. Water boils at a lower temperature, which is why cooking instructions change at altitude. Push the pressure low enough, and the boiling point falls all the way down to the temperature you already are. Mars sits at 6. The Armstrong limit is 63. That planet's entire atmosphere is roughly 10 times below the threshold. So, on the surface, unprotected. The moisture on your eyes and on your tongue and in the lining of your lungs would begin to vaporize. Not because it is hot, because there is nothing pressing back. Let your jaw unclench. Nobody is out there. I want to correct the popular version of this immediately, because films have done a lot of damage. You would not explode. Human skin is a genuinely impressive containment vessel, and it holds what actually happens. Based on the small number of accidental vacuum chamber exposures and on animal studies, is that the body swells considerably. Consciousness is lost in something on the order of 15 seconds as oxygen leaves the blood in the lungs, and the situation becomes survivable only if pressure is restored within a couple of minutes. That is the honest account. It is not cinematic. It is much quieter and much faster than the movies suggest. And note the direction of the danger, because this is the part that reframes everything. The problem is not that something is coming at you. The problem is that something has been removed. There is no attack. There is only absence. Now the second half of the picture, which is temperature, because it also does not behave the way a desert would. The average surface temperature on Mars is around -60 degrees Celsius, which is about -80 Fahrenheit. That is cold, though not unimaginably so. Antarctica has recorded temperatures below -80 Celsius, and human beings have worked in those conditions. But the average is misleading, and the swing is the story. Measurements from surface missions have found that on a summer day near the equator, the ground can warm to something above 0 Celsius, while the air a couple of meters above it stays far colder. And then, within hours of sunset, everything falls away toward -70 or lower. A daily swing of many tens of degrees is ordinary. Why so extreme? Because the atmosphere is too thin to hold heat. On Earth, air is a blanket. It absorbs warmth during the day and gives it back slowly at night, which is why a temperate evening does not plunge to freezing the moment the sun goes down. Water, in particular, in the air and in the oceans, is superb at storing heat. Our planet has enormous thermal inertia. Mars has very little. A thin skin of carbon dioxide cannot store much of anything. So when the sun is on the ground warms. When the sun leaves, the heat radiates straight out into space with almost nothing to slow it. And the temperature collapses, which means the environment is not stable. It is a place that lurches every single day. And repeated thermal cycling of that magnitude imposes real stress on structures, seals, electronics, and any exposed mechanism, which is one of the standard headaches in designing anything intended to last there for years. Everything in this chapter is measured, and cleanly so. Pressure, composition, temperature range, the Armstrong limit. These are among the most thoroughly confirmed measurements in planetary science, taken by multiple independent spacecraft from multiple countries across 5 decades. And they agree with each other. There is no controversy here at all. That is exactly why this chapter matters. Because here is the conclusion. Everything else we discussed tonight happens inside a sealed container. Every single thing. The habitat, the greenhouse, the workshop, the place where someone sleeps, and the place where someone eats, and the place where two people have an argument, all of it takes place inside a vessel holding roughly 1 atmosphere of pressure against roughly nothing, with a wall between the two. Forever. On Earth, a building keeps out weather. If a window breaks, you are cold and inconvenienced, and the rain comes in. On Mars, a building keeps out the absence of everything. If a window breaks, you have a number of seconds, not minutes. The habitat is not a house. It is a submarine that never surfaces. Consider that everyone who has ever lived aboard a submarine or a space station has done so knowing there was a surface, a door, an eventual outside. The International Space Station has been continuously occupied since November of 2000, which is a genuinely magnificent achievement. And every single person aboard it has been about 400 kilometers from breathable air, with a vehicle attached that could bring them home in hours. On Mars, the nearest breathable air is a 7-month journey away, and the road home is on that same 2-year timer. Now, we have spent 4 chapters taking that place apart, and I have been describing it entirely in numbers, which is a kind of dishonesty of its own, because a person standing there would not experience 6 millibars. They would experience a morning. So before we go any further into the survey, I want to stop analyzing and simply take you outside and let you look. Put the clipboard down for a while. For this one chapter, nothing needs assessing. We are not looking for defects. We are going to walk out onto that surface and stand still. And I am going to tell you what would actually be around you. Let me be honest about what this chapter is, because I promised in the first hour that I would always tell you where the line runs. The scene is a reconstruction. I am choosing a season and a landscape and putting an imaginary person in it and describing what their body would do. That part is invention, in the ordinary sense that any illustration is invention, but every physical detail inside the scene comes from somewhere real. It is either a direct measurement returned from Mars by an instrument, or it is a straightforward consequence of that planet's measured gravity and atmosphere. Nothing here is decorative. Nothing is guessed at for effect. When I describe the color of the sky, a camera photographed that color. When I describe how sound behaves, a microphone recorded it. So this is an illustrated reconstruction built on measurements. That is the honest label. And, with it in place, we can go outside. It is morning. Let it be late spring in the northern hemisphere. Somewhere on a wide crater floor with low hills on the horizon. Look up first. The sky is not black, and it is not the salmon pink of the old book covers either. It is closer to butterscotch, a soft, dusty, yellowish brown, glowing faintly, because there is always fine dust suspended in that thin air, and it scatters the light in a way that fills the whole dome of the sky with a warm haze. On a clear day, it is paler and more golden. During a dust season, it deepens toward a heavy tan, and the light on the ground goes flat and shadowless, the way it does here under a thick overcast. Now find the sun. It is there, and it is smaller. From Mars, the sun appears about 2/3 the width it does from Earth, because you are roughly half again as far away from it. It is still far too bright to look at directly, but it is noticeably a smaller disk in a much larger sky. And the light it throws down is dimmer. Mars receives roughly 43% of the sunlight that reaches us, and the dust in the air takes more of it. A clear Martian noon would be a good deal darker than a clear noon at home. Not dark, not gloomy, closer to a bright, hazy, overcast day than to full sunshine. And it never reaches the brilliance of an ordinary sunny afternoon here. That is the first thing that would tell a body something was different. Not the cold, which the suit handles, the quality of the light, permanently softened, permanently a little tired, everywhere on the planet, in every season. Now look at the ground. It is not really red. Up close, in the images returned by every rover that has ever sat on that surface, it reads as a range of browns and ochres and dull oranges, with grey rock underneath wherever something has been scraped or broken open. The red is a coating, iron oxide, dust, spread across everything by wind over an extremely long time. Break a rock in half on Mars, and the inside is often grey. The ground is covered in stones of every size, sorted and scattered by wind, and between them the dust lies in soft drifts. Wheel tracks left by rovers stay visible for years, because there is no rain to erase them, and the wind only slowly fills them in. Now the part that would genuinely unsettle a visitor, and it is not visual at all. Listen, in February of 2021, the Perseverance rover landed carrying 2 microphones. And on the 19th of February, the day after touchdown, one of them recorded the first sounds ever captured on the surface of another planet. An international team, led by Sylvestre Maurice, published the first analysis of that soundscape in the journal Nature on the 1st of April, 2022. What they found was strange enough that even the researchers had not fully expected it. On Earth, sound travels at about 343 meters per second, and that speed does not meaningfully change with pitch. A trumpet and a bass drum reach you together. On Mars, low sounds travel at about 240 meters per second. Sounds above roughly 240 hertz, which is a pitch a little below middle C, travel about 10 meters per second faster. Mars has 2 speeds of sound. The reason is the carbon dioxide. At that low pressure, those molecules cannot shed their vibrational energy fast enough to keep up with the higher frequency waves. And the effect is that treble outruns bass. So, if someone spoke to you from a few meters away in that thin air, the high parts of their voice would technically arrive slightly before the low parts. In practice, you would barely notice, because something else dominates: the silence. Sound in that atmosphere is enormously attenuated, and the higher the pitch, the faster it disappears. For the kinds of sounds the Perseverance team was able to study, sound faded away over a distance you could walk in a few seconds, and the high frequencies were gone well before that. On Earth, a comparable sound would still be reaching you many times further away. So stand on that crater floor, and everything more than a short walk away is essentially not there acoustically. No distant sound of anything. No horizon full of faint noise the way every landscape on Earth has. Even the quietest desert. Your own breathing in the helmet, the sound of your own suit, and beyond that, a close, muffled quiet, extending in every direction to the edge of the world. The research team described it plainly. Mostly, a deep silence prevails. You are allowed to just look. There is nothing here to assess. Now, take a step. You weigh about 38% of what you weigh in that bed. A person who is 70 kilograms here is around 26 there. The suit adds a good deal back, which is one of the small ironies of the place. But the fundamental sensation is of being much lighter and, more strangely, of falling more slowly. That second part is what would take longest to learn. Drop something from waist height here, and it lands in about half a second. En masse, from the same height, it takes roughly 60% longer. Not dramatically slow, just consistently, persistently wrong. Every tool, every glove, every dropped sample bag, descending at a pace your hands did not predict, so that you reach for things a beat too early for the first several weeks. Jumping is the other way around. You rise higher, and you hang, and you come down unhurried. The Apollo footage gives some sense of it at 16% gravity, where the astronauts developed that loping, bouncing gait because ordinary walking simply did not work well. At 38%, it would be less extreme, probably closer to a long, floating stride. And nobody has ever done it. So the details are genuinely unknown. And when something lands, the dust it disturbs rises and settles in a way that has no earthly equivalent. Governed by weak gravity, extremely fine particles, and an atmosphere thin enough that ordinary intuitions about how dust behaves simply do not apply. The same planet that lets a tool fall slowly also raises dust storms that can wrap the entire world for weeks. Nobody should trust their instincts about Martian dust. And we will come back to it, because it turns out to matter a great deal. Now stay until evening, because the evening is the thing. Sunsets on Mars are blue, not the sky. The sky stays butterscotch, but around the setting sun there is a distinct cool glow, a patch of blue-grey light spreading out from the disk as it drops toward the hills. Rovers have photographed this repeatedly, from Spirit and Opportunity onward, and it is one of the few Martian images that genuinely does not resemble anything on Earth. The cause is the dust. Fine particles of a particular size scatter red light broadly across the sky, which is what gives the daytime that warm tan, and they let blue light pass more directly forward. So near the sun, where you are looking almost straight through the dust toward the source, blue survives the journey and everything else has been scattered away. We have exactly the opposite arrangement. Our sky is blue and our sunsets are red. Theirs is the mirror image, for the same physical reason running the other way. Something worth sitting with. Every sunset any human has ever watched, on every evening of every life that has ever been lived, has been some variety of red or gold. There is one place we know of where the light goes the other way, and it has been doing it, unwatched, every single evening for 4.5 billion years. The blue glow lingers a while after the sun is down. Twilight on Mars lasts longer than you might expect, because that suspended dust catches sunlight from below the horizon and holds it in the sky. Then the temperature begins its fall, and the sky darkens, and stars come out through an atmosphere far thinner than ours, though still carrying enough dust to soften them. And if you knew exactly where to look, you would find one particular star. Earth from Mars is a bright point of light in the twilight, sometimes with an even fainter point beside it, which is the Moon. Curiosity photographed it in 2014 from the surface. It is not spectacular, It is a bright star, low down, in the evening or the morning, depending on the season. That is what home looks like from there. A star with a smaller star beside it. Every physical fact in that scene came from an instrument. The sky color, the light level, the 2 speeds of sound, the way it fades, the blue sunsets, the view of Earth. This is a real place, with real mornings and real evenings. And it has been having them without interruption while nobody watched. That is worth holding on to as we go back to the survey. Because everything from here on is going to be about why you cannot stay out here. And it would be easy to forget that there is a genuine somewhere out here to not stay in. The clipboard comes back up now, and the first thing on it is the reason that butterscotch sky is a problem. Picture the dome. You have seen it 100 times. It appears on book covers and in concept art and in nearly every film about this subject. A transparent geodesic shell standing on red ground, with a green interior visible through the glass. Trees inside, a curved path and a bench, and through the roof, that sky we just stood under, and the small sun, and at night a scattering of stars over the sleeping town. It is a genuinely beautiful image, and I do not want to take it from you carelessly. It has done real work in the world. A great many people who now build spacecraft for a living first fell in love with this subject because of a painting like that. But we are surveying the house, and this is the room where the survey and the painting disagree. Put the 2 shields back on the table, the column of air above your roof, and the magnetic field generated by moving iron in the core of this planet. Mars has neither. The atmosphere we measured provides a little shielding, and it is worth saying that it is not 0. It has some mass, and mass is what matters. But it is roughly 1% of Earth's atmospheric column, and it does not begin to do the work ours does. The magnetic field is the more interesting absence. Mars almost certainly had one once. In 1997, and afterward, NASA's Mars Global Surveyor mapped the magnetism of the crust and found something remarkable. Large regions of ancient rock in the southern highlands are strongly magnetized, in stripes, frozen into the stone. That is the signature of rock that solidified in the presence of a global magnetic field. And it means that early in its history, Mars had a working dynamo in its core, just as Earth does now. For reasons still being investigated, that dynamo shut down early in the planet's history. The timing and the mechanism remain active research questions. What remains is only fossil magnetism, locked in old rock, patchy and local, with no global structure to it at all. There is something quietly sad in that. If you let it be, a planet that once had a heart doing the same work our planet's heart is doing right now, above your bed, at this moment, and then it stopped, and the sky was open after that. That happened a very long time ago, and it is finished. So the radiation we discussed during the crossing does not stop when you land. It continues arriving at the surface, reduced somewhat by that thin atmosphere and by the fact that the planet itself blocks the entire downward half of the sky, but arriving nonetheless. And once again, we do not have to guess, because the instrument kept running. The radiation assessment detector aboard Curiosity has been operating on the surface of Mars since August of 2012. Hassler and colleagues published the surface results in December of 2013. Across the period from August 2012 to June 2013, the average galactic cosmic ray dose equivalent rate at the surface was 0.67 millisieverts per day. Place that beside your own life. Around 2 to 3 millisieverts a year. Naturally, on Earth, on Mars, unshielded on the surface, you would receive a year of natural background in about 4 or 5 days. Multiply it across a 500-day surface stay, and you get something in the region of 300 millisieverts from the stay alone, on top of the 660 from the round trip, which is how the mission total arrives near 1 sievert. That is the number if you stand outside. Nobody would. So what do you do about it? The answer that a great many long-duration studies have converged on, independently, from different countries and different decades and different funding agencies, is broadly the same answer. You put mass over your head, and the mass available in useful quantities is the ground itself. The Martian surface is covered in regolith, the broken rock and dust and fine-grained material lying over the bedrock. It is free. It is everywhere. It has no other use. And several meters of it, piled over a habitat, provides genuine and substantial protection, because shielding is fundamentally about how much material a particle has to traverse. Estimates of the required thickness vary with the assumptions, but figures in the literature tend to run from around 2 or 3 meters at the low end to 5 or more for serious long-term protection. Some studies favor lava tubes instead, natural tunnels left behind by ancient volcanic flows, of which Mars appears to have many, some of them enormous. In that case, the planet has done the excavation for you. I want to be accurate about how universal this conclusion is, because it is easy to overstate. Not every design buries everything. There are architectures that rely on limited surface time plus a heavily shielded storm shelter. There are proposals using water walls, or hydrogen-rich polymers, or combinations of mass placed only where people spend the most hours. Short-duration missions can accept a good deal more exposure than a permanent settlement can. But the direction of travel is consistent for anything meant to last years. The main living spaces end up covered with substantial mass, most often regolith or natural subsurface formations. The habitat goes underground or under a mound, not the dome, not the glass, not the trees visible through a transparent roof against that sky we just stood beneath. The radiation measurement is solid. 0.67 millisieverts per day at Gale Crater. Published and confirmed. The physics of shielding by mass is solid too. Exactly how thick, for exactly what risk tolerance, using exactly what construction method, and at what cost in equipment and time and energy, is very much an open engineering question that different groups answer differently. And now the thing this chapter is actually about, because the number is not really the point. The point is what kind of life this implies. Consider what you are picturing when you imagine living somewhere, almost certainly, somewhere in that picture. There is a window, light coming in at a particular angle in the afternoon. The knowledge, even when you are not looking, that outside exists and is nearby and can be entered at will. Now take that out. A shielded Martian habitat is a structure where the outside is not simply dangerous. It is dangerous cumulatively, invisibly, and without sensation. That is the part I find strangely difficult. Radiation gives you nothing to feel. There is no cold, no pressure, no smell, no warning. You could stand out there in a perfectly functioning suit, entirely comfortable, watching that blue light spread out from the setting sun. And the only thing happening is a slow accrual on a total that will never go down, which means every trip outside becomes an expenditure, not of energy or supplies, but of a lifetime budget that has been allocated to you and can only be spent. Think what that does to ordinary decisions. On Earth, going outside is free. It is what you do when you are restless, when a room feels too small, when you need 5 minutes away from someone. There, going outside costs something permanent, and someone is keeping track. Every settlement design includes dosimetry. Somebody, somewhere, has a running total for each person. And windows become genuinely difficult. Transparent materials shield poorly compared to their mass. There are workable compromises, and small viewports, and the entire modern solution of high-resolution screens fed by outdoor cameras, which is not nothing. The station has a cupola and the astronauts love it. And Mars habitat designs do include ways to see out. But the default condition, the shape the engineering keeps insisting on, is a covered volume. I want to be careful not to overstate this into misery, because that would be its own kind of dishonesty. Human beings live in submarines for months. People overwinter at Antarctic stations in continuous darkness. Miners work underground for entire careers. We are considerably more adaptable than the romantic version of ourselves suggests. And the people who go will be selected and trained and will have chosen it freely. But notice the quiet reversal that has happened over the last 2 chapters. We spent a whole chapter standing outside, under that soft golden sky, watching a blue sunset in the deepest silence in the solar system. And the engineering says the correct place to experience that is on a screen from under 4 meters of rock. The dream was the view. The engineering says the view is the hazard. So the settlement is covered, and the people are shielded, and the sky is something you look at through a camera, which would be almost manageable if the outside stayed outside. It does not. Let me start with an old story, because it is the best evidence we have, and it has the advantage of having actually happened. December 1972. The lunar module Challenger, sitting in a valley called Taurus Littrow, with mountains on 3 sides higher than anything in the Rockies. Harrison Schmitt is inside it, and he has just taken his helmet off. Schmitt is a trained geologist, the only professional scientist ever to walk on another world, and he has spent the day doing exactly what he was sent to do. He and Eugene Cernan have been outside collecting samples, driving the rover, kneeling in grey powder that covers everything. Over 3 excursions, they will spend more than 22 hours out there, and every time they come back inside, the dust comes with them. It is on the suits. It is ground into the fabric, at the knees and the gloves. It clings by static charge and will not brush off properly. They have used a brush. It did not really work. Now the hatch is closed. The cabin is repressurized. And all that dust, which was floating in the returned air, is suddenly available to breathe. Schmitt reacts to it. Congestion, a stuffy nose, irritation in his throat and eyes. In the mission transcripts, He describes it in terms of hay fever, and the phrase lunar hay fever entered the record because of him. The symptoms fade within hours each time. That was 3 days. 3 days. On the most carefully planned expedition in history. And the crew could not keep the dust out of their lungs. Now, hold that up against 500 days. This is a chapter about small things. And small things are easier to hear about when you are comfortable. So take a moment to be comfortable first. There are 2 separate problems on the Martian surface, and they are usually confused with each other. One is a mechanical nuisance. The other is a genuine medical concern. The first is the dust itself. I want to be careful here, because the easy move is to treat Martian dust as lunar dust with a different color. And that is not accurate. Lunar dust is a special case. The moon has essentially no atmosphere, no wind, no water, and no ordinary weathering of any kind. Its particles are shaped almost entirely by micrometeorite impacts, which leaves them jagged and glassy and extraordinarily abrasive. That is why Apollo had the problems it did. Mars is different. Mars has wind. It has dust storms that can wrap the entire planet. It has particle transport, and a long history involving liquid water, and genuine chemical alteration of minerals over billions of years. Its dust has been worked on. What is well established about Martian dust is that it is extremely fine, with typical particles only a few micrometers across, that it is easily lifted and carried by wind despite that thin air, that it becomes electrostatically charged and clings stubbornly to surfaces, and that its chemistry is quite different from anything lunar. So the honest framing is this: the Apollo experience does not tell us what Martian dust would do inside a habitat. What it demonstrates is how difficult extraterrestrial dust is to keep outside one, even on a 3-day visit with a highly trained crew. The engineering evidence from Mars itself is substantial in its own right. Both Spirit and Opportunity were solar-powered, and dust settling on their panels was a permanent, gradual drain on available energy across their entire missions. Occasionally, the wind cleaned the panels, and the teams called these cleaning events and were genuinely delighted by them. Rover cameras, bearings, seals, and moving joints all deal with it constantly. And in 2018, a planet-encircling dust storm dimmed the sky over Opportunity so severely that the rover, already many years past its planned 90-day mission, went silent and never woke up. It is worth being accurate about that. The end was not simply dust on the panels. It was a sustained loss of sunlight during the storm, combined with cold and the cascade of problems that follows a power failure in a very old machine. Dust degraded the power system and contributed to conditions that ended the mission. That is, dust as an engineering problem, well documented, manageable with effort. And every serious design includes elaborate dust mitigation at the airlock. Now the second problem, which matters more. In 2008, NASA landed a small stationary lander called Phoenix in the northern plains of Mars. It carried a chemistry laboratory designed to analyze soil, and it did something no previous mission had done in the same way. It scooped up Martian soil, mixed it with water brought from Earth, and measured what dissolved. What it found, reported by the Phoenix science team with Michael Hecht of the Jet Propulsion Laboratory among the lead authors, in a 2009 paper in Science was perchlorate. Perchlorate is a chemical compound, a chlorine atom bound to 4 oxygen atoms. On Earth, it exists naturally only in small quantities in very dry places such as the Atacama Desert, and industrially as a component of rocket propellant, fireworks, and some fertilizers. At the Phoenix landing site, it appeared to make up something in the region of 0.5% of the soil by weight. Subsequent measurements by Curiosity found chlorine-bearing compounds consistent with perchlorates at Gale Crater as well, a very different location. Thousands of kilometers away, the current picture, and this remains an area of ongoing research rather than a closed question, is that perchlorates are probably widespread in Martian soil rather than a local peculiarity of one site. So what does perchlorate actually do? Here is the honest medical account. Perchlorate interferes with the thyroid gland's ability to take up iodine. The thyroid needs iodine to make the hormones that regulate metabolism throughout the body, and perchlorate competes with iodine at the point of uptake. Sustained exposure can therefore reduce thyroid hormone production, and thyroid hormone matters a great deal for development, for metabolic regulation, and for cognitive function. This is not exotic toxicology. It is well established, and it is precisely why perchlorate contamination in drinking water is a regulated environmental concern in the United States and elsewhere. Let me be careful, because this is where these videos slide into drama. Perchlorate is not a fast-acting poison. Nobody collapses. There is no dramatic scene. It is a chronic exposure concern. And the relevant question is about long-term ingestion or inhalation at low levels over months and years. That is a real concern. And it is a different sort of concern from the one the word poison usually conjures. And there is a second point of honesty. Perchlorate is also, in a strange way, useful. It is an oxidizer. There are serious proposals to extract it and use it. And there are bacteria on Earth that metabolize it, which has led to genuine research into biological remediation of Martian soil. A hazard and a resource are frequently the same substance viewed from different angles. But combine the two problems, and you see why this chapter exists. You have a fine, clingy, electrostatically charged dust, which the Apollo experience suggests will be very hard to keep outside. And that dust, en masse, appears to contain a compound with known chronic thyroid effects. The dust is not a problem outside. Outside, you are in a sealed suit. The dust is a problem inside, in the place where people take off their helmets and eat their meals and sleep for the next 500 nights. This is why airlock design has become a serious research area, and it has produced one of my favorite pieces of thinking in the whole subject, the suit port. The idea is that the suit never comes inside at all. It is mounted permanently on the outside of the hull, sealed against a hatch, and the person climbs in through the back of the suit from within the habitat and then detaches. When they return, they dock the suit back onto the hull and climb out through the back, leaving the entire dusty exterior permanently outside. It is elegant. It has been prototyped and tested in analog environments. It is not a full solution, because tools and samples and equipment still have to come in somehow. And every seal is a place where something can go wrong, but it shows the level at which people are working. So where does this line of the report stand? The presence of perchlorate in Martian soil is measured. Phoenix in 2008. Published in 2009. Supported by later evidence from curiosity. The behavior of Martian dust is measured from decades of rover operations. The health effect of perchlorate on humans is measured from terrestrial medicine and environmental regulation. And now we arrive at the first genuine blank line of the night. And I promised I would always name them. Nobody has ever run this experiment. There is no data anywhere on what happens to a human body exposed to low levels of Martian dust, containing Martian perchlorate concentrations, in a sealed habitat atmosphere, over a period of 500 days. Not tested and found safe. Not tested and found dangerous. Never tested. The exposure model does not exist because the exposure has never occurred. Notice how that feels different from everything before it. Radiation. We can calculate. Landing mass. We can test. Those obstacles have edges. This one is a line in the survey report where the inspector writes that the material appears to be present in significant quantity throughout the property and that no assessment of long-term occupant exposure has ever been performed. Everything before this was about forces, gravity, pressure, energy, mass, things that push and pull, that can be resisted with sufficient engineering. This chapter was the first one about the body, about something small and gradual, getting inside a person and staying there. And it will not be the last. Because there is one more thing waiting on that surface that gets into every cell of a human being. Continuously, from the moment of arrival, it cannot be filtered at an airlock. It cannot be sealed against. It passes through walls of any thickness, and through rock, and through the suit, and through the skin. And there is no proposed technology anywhere that shields against it. It is the weight of the planet itself. This is the chapter I have been walking toward all night, and there is no hurry at all. If you drift off during this one, you will have drifted off during the part of the survey that matters most. And I can think of worse ways to fall asleep than inside a genuinely open question. Let me begin with something happening to you at this exact moment. You are being pulled downward. Every cell in your body is. It has been true continuously since before you were born, and it will be true for as long as you exist on this planet. And you have never once perceived it as a force, because you have never experienced its absence. But your body has perceived it constantly. Your skeleton has spent your entire life in a quiet negotiation with that pull, laying down bone where load is applied and quietly removing it where load is not. Your heart has spent your entire life pumping against it, sized and shaped and calibrated to lift blood upward from your feet to your head against a gravitational gradient. The fluids inside you distribute themselves according to it. The little organs of balance in your inner ear are built entirely around detecting it. The muscles of your legs and back exist in the proportions they do because of it. Gravity is not something your body is subjected to. It is something your body is made of. Now, let me tell you what we actually know about what happens when you take it away. We know a great deal. And the reason is that human beings have been living in orbit almost continuously since November of 2000. Before that, there was Mir, and Skylab, and Salyut. Taken together, this represents decades of accumulated human time in weightlessness, studied more carefully than almost any other physiological condition in the history of medicine. Here is the picture, that emerged. Bone density falls. In microgravity, the skeleton stops receiving the load signal it has always used to decide how much bone to maintain, and it begins to reabsorb material it no longer appears to need. The commonly cited figures put the loss in weight-bearing bones, the hips and the spine and the legs, at something in the region of 1 to 1.5% per month, with considerable variation between individuals and between specific bones. Sit with that rate. 1% a month sounds small and is not. Over a 6-month mission, it becomes 6 or more % from the parts of the skeleton that hold a person upright. It is the reason exercise aboard the station is not optional and not recreational. Crew members spend on the order of 2 hours a day strapped into resistance and treadmill equipment, and that regimen exists specifically to slow this process. It works. Partially. It does not stop it. Muscle atrophies for the same reason. Nothing is asking the legs to do anything. The cardiovascular system reorganizes. On Earth, gravity keeps a substantial volume of your blood pooled in the lower body, and your heart works against that. Remove gravity, and the fluid redistributes upward. Crew members arriving at the station notice puffy faces and thin legs within days. The body, sensing an apparent surplus of fluid in the chest and head, responds by reducing total blood volume. The heart, no longer lifting anything, can lose mass. And then there is the one that genuinely surprised people. And it is worth naming because it shows how much of this we did not anticipate. Vision changes. Beginning in the late 2000s, flight surgeons noticed that a substantial fraction of long-duration crew members were coming home with altered eyesight, and imaging showed real structural changes, including flattening at the back of the eyeball and swelling of the optic nerve head. NASA gave it the name Spaceflight-Associated Neuro-Ocular Syndrome. The leading explanation involves that upward fluid shift and pressure changes inside the skull, though the full mechanism is still being worked out. And for some individuals, the changes have not fully reversed after return. That last detail is the important one. We found this by accident. Decades into human spaceflight, in the best studied environment we have. Nobody predicted it. It was simply there, waiting, in the data of people's actual eyes. Now, here is the sentence this entire chapter exists to deliver. Every single thing I have just told you is about zero gravity. Mars is not zero gravity. The surface gravity of Mars is about 38% of Earth's 0.38 g. A person weighing 70 kilograms here would weigh about 26.5 kilograms there. Not floating, not weightless, just lighter, permanently, in exactly the way we described standing out there in that crater, watching things fall too slowly. And we have no idea what that does to a human being over years. Let me be extremely precise about this claim, because it is the single most important claim in this entire video, and I do not want a shred of exaggeration in it. We have excellent human data at 1G. That is the entirety of human medicine. Every study ever done. All of it conducted at the bottom of this particular gravity well. We have very good human data at approximately 0G, decades of it, from hundreds of individuals, some for a year or more at a time. Between those two values, at 0.38 G, or at the Moon's 0.16 G, or at any other fraction, the human dataset is empty, not thin, not preliminary, empty, 12 human beings have walked on the moon at 16% gravity, and the longest anyone stayed on that surface was about 3 days. 3 days does not produce physiological data on bone remodeling. That is not a criticism of Apollo. It simply was not that kind of mission. So, the honest state of knowledge is that no human being has ever spent more than a few days in any gravitational environment other than 1G or 0G. This is the missing data point. And now, let me explain why the emptiness of that gap is so much worse than it sounds. Because most people assume the answer must be interpolation. The intuitive assumption is that the effects scale 0G causes a certain amount of bone loss. 1G causes none. Therefore, 0.38G should cause roughly 62% of the 0G effect. Draw a straight line between the two known points and read off the middle. There is no scientific basis for that line. Biology is full of thresholds. Bone remodeling responds to mechanical loading, and loading responses in living tissue are frequently not linear at all. It is entirely possible that there is a threshold effect, and that some fraction of Earth gravity is sufficient to maintain the skeleton nearly normally, in which case Mars might be almost fine. It is equally possible that the response is closer to binary in the other direction, and that anything meaningfully below 1G produces most of the deterioration seen in orbit. It is possible that different systems behave differently. That bone finds 38% adequate, while the cardiovascular system does not. Or the reverse. All of those are plausible. None of them can be chosen between with the data we have. Because we do not have the data. We do have some animal work, and it would be dishonest to imply the shelf is entirely bare. There have been centrifuge experiments with rodents in orbit going back decades. Spinning cages at partial gravity levels aboard spacecraft. Those experiments have produced useful hints, and they generally support the idea that partial gravity is better than none. But rodent skeletons are not human skeletons. The sample sizes have been small, the durations short, and no rodent has ever been raised through a full life cycle at Mars gravity either. So the state of the report on this line, the 0G effects are measured extensively. The Martian gravitational value is measured to high precision from orbital mechanics. The effect of 0.38G on a human body over 500 days, or a decade, or a lifetime, has never been tested by anyone, anywhere, ever. And now, the consequence that makes the mission architecture uncomfortable rather than merely uncertain. Remember the shape of the journey. 6 to 9 months in weightlessness on the way out. Then 500 days at 38% gravity. Then 6 to 9 months in weightlessness, again on the way home. Consider the moment of arrival at Mars. A crew that has spent most of a year in 0G, with whatever bone and muscle and cardiovascular deconditioning that produced, has to land a vehicle and then function. On Earth, returning station crews are carried out of the capsule. They are met by teams, placed on stretchers, taken to medical facilities, and given weeks of supervised rehabilitation. That is standard, and it is not considered a failure. It is what the body needs after that experience. On Mars, nobody is waiting outside. Whatever the crew has to do in the hours after landing, they do in that condition, on a surface that has never been rehearsed, at a gravity level nobody has ever adapted to. The 38% helps. Of course, it is far kinder than arriving back on Earth at full weight. That is a genuine point in favor, and I want it stated. But you can see the shape of the problem. It is not one transition. It is 3 in a row, across 3 years, with an untested middle stage. Let me close by saying the thing I actually believe about it, clearly marked as my own view rather than as a finding. I do not think this is the terrifying problem. I think it is the clearest illustration of what terrifying actually means in this survey. Not danger. Ignorance. In a place where ignorance cannot be resolved cheaply. Because notice the shape of the trap. The only way to fill this gap in the data is to put human beings in partial gravity for a long time and observe what happens to them. Which means the experiment that would tell us whether it is safe to go is the same experiment as going. There is a way out, and it is worth knowing about. A centrifuge would do it. A rotating facility in orbit, spinning to produce artificial partial gravity, with people living inside at 0.38 g for a year while we watch. It has been proposed many times, in many forms. Since the earliest days of station design, it has never been built, largely because of cost and mass, and the fact that it competes for funding against missions that produce more visible results. So the answer is obtainable. We simply have not obtained it. That is a strange and quiet thing to hold. Lying in the dark. There is a specific fact about human bodies, one that determines whether an entire branch of the future is possible, and it is sitting out there, entirely knowable, waiting for someone to build the machine that asks the question. None of that needs resolving tonight. It has waited 50 years already. Let your body go heavy into whatever is holding it up, and be glad, for a moment, of the exact weight it has. We are halfway through the house now. The road, the radiation, the landing, the air, the surface itself, the shelter, the dust, and the body. The rooms that remain are the ones nobody thinks to inspect until they have already moved in. What happens when a person gets sick? Whether the air can be made to cycle forever without help, what anyone would actually eat, and, eventually, what it means that a place where people stay is a place where people are born. But that is for the second half of the night. Let me give you the number first, and then show you what it does. A radio signal from Mars to Earth takes between about 4 and about 22 minutes, depending on where the two planets are in their long cycle. A question and its answer take between 8 and 44 minutes to complete a round trip. That is not a technological limitation. This is the part people find hardest to accept. So let me be direct. That delay is not a matter of better antennas or more powerful transmitters or a superior network. It is the speed of light. It is the maximum rate at which any information of any kind can move between 2 points in this universe. And nothing anyone builds will ever improve on it. Every other obstacle in this survey has an engineering path. However difficult, this one has none. It is fixed by physics. Permanently. For as long as there are human beings, and as long as those two planets are that far apart. Now, let me show you what it means in a room. Nobody in this chapter is real, and nobody is unwell tonight. This is a scenario, examined in advance by careful people, which is exactly what scenarios are for. Imagine a small pressurized volume buried under several meters of regolith. 6 people, or 8, some months into a 500-day surface stay. One of them has been unwell for a day and a half. There is pain in the lower right of the abdomen, and it has migrated there from around the navel, which is the classic pattern. And there is a low fever now. On Earth. This is one of the most routine emergencies in all of medicine. Appendicitis affects something in the region of 1 person in 15 over a lifetime. In any decent hospital, it is a straightforward operation with an excellent outcome, and the patient is usually home within a day or two. In that buried room, here is what happens. Somebody, most likely the crew member with the most medical training, examines the patient. They may have an ultrasound, because ultrasound is compact and has flown in space for years and is genuinely useful. They will not have a CT scanner, because a CT scanner weighs as much as several people and draws power accordingly. And we have already established what mass costs to land. They form an opinion, and then they ask for help. The question goes up to the antenna and out across the gap. Somewhere between 4 and 22 minutes later, it arrives on Earth, where a flight surgeon reads it, considers it, perhaps consults a surgeon, and composes a response. And that response takes another 4 to 22 minutes to travel back. Best case, most of an hour has passed before the first meaningful exchange completes. Worst case, considerably more. And that is one exchange. A real medical consultation is not one question. It is a conversation. 20 exchanges deep, with follow-ups and clarifications and changes of mind as new information arrives. There is no conversation available. There is only correspondence. So the decision is made in the room. It has to be. Whatever expertise exists on Earth can inform that decision, slowly, at a lag. But the person holding the instrument is the person who decides. And now, the harder part. There is no evacuation. I keep returning to this because it is the most alien feature of the whole scenario, and it is easy to hear without absorbing. Every extreme environment human beings currently work in has an evacuation plan, and those plans get used. When a crew member aboard the International Space Station has a serious medical problem, the vehicle is attached, and the trip home is measured in hours. This is not hypothetical. In 2018, a Soyuz launch failed shortly after liftoff, and the crew were on the ground within minutes. Antarctica is the closer analogy, and the stories there are worth knowing. In 1999, Dr. Jerry Nilsson, the physician at the Amundsen Scott South Pole Station, discovered a lump in her own breast during the winter. When no aircraft can reach the pole, she performed a biopsy on herself, assisted by colleagues with no medical training, guided by consultations over a satellite link. Chemotherapy drugs were airdropped in July, in the dark, in extreme cold, by a military aircraft that could not land. She was evacuated in October, as soon as conditions allowed. In 2016, in another winter emergency, 2 aircraft flew to the South Pole in June darkness to evacuate a sick station worker. It is a flight that had only been attempted a handful of times in history. I tell you those stories because of what they have in common. In both cases, the isolation was profound. And in both cases, eventually, something came. It took months. It was extraordinarily difficult. People risked their lives to do it. But there was a direction in which help could travel. And it did. En masse. That direction is closed for a minimum of many months and realistically for a year or more. Because the road home is on that same 2-year timer and no amount of urgency will move it. There is no aircraft that can be sent. There is no ship that can turn around. The nearest hospital is on a planet that is currently on the far side of the sun. The signal delay is measured. It is arithmetic performed on the speed of light and the distance between two orbits. The impossibility of timely evacuation is measured. It follows directly from the orbital mechanics we walked through at the beginning. The medical incidence rates are measured. We know approximately how often appendicitis and kidney stones and dental abscesses and fractures occur in populations of a given age and health. And those rates are not zero even among screened, healthy, exhaustively examined individuals. Where the disagreement lives is in what should actually be done about it. The proposals are real and serious. Prophylactic appendectomy has been discussed for decades in the aerospace medicine literature, meaning removal of a healthy appendix before departure specifically to eliminate the risk. It has actually been a requirement in some Antarctic programs historically. Comprehensive dental work before flight is standard practice already. Crew selection screens out known conditions. At least one crew member with substantial medical training is assumed in every architecture. And there is genuine discussion of surgical capability aboard. But every one of those measures reduces the probability rather than removing it. You can remove an appendix. You cannot remove the possibility of a stroke, or a fracture, or a cancer too small to see on the pre-flight scan, or a psychiatric emergency, or something nobody anticipated because it has never happened to a human at 38% gravity. And that is the connection back to the last chapter, and why these two belong together. We do not know what partial gravity does to a body over a year and a half. So we do not know what medical events to prepare for. The pharmacy has to be packed years in advance, at a fixed mass budget, by people making educated guesses about what will go wrong in a physiological environment no human has ever inhabited. Notice, though, that this chapter is not really about medicine. It is about a thing being removed that you have never once thought about. There is a background assumption you have carried all your life, so quietly that it has never surfaced as a thought. It is the assumption that if something goes badly wrong, someone can come, not that they will succeed, simply that the possibility exists, that there is a number to call and a direction that help arrives from. That assumption is so foundational that we do not experience it as a belief. We experience it as the shape of the world. Take it away, and something changes in the character of ordinary life. Not dramatically. Most days, nothing happens and the assumption is never tested, on Mars or anywhere else. But it sits underneath everything. That is the true content of this chapter, not the risk of appendicitis, the permanent, quiet, structural absence of rescue. So, let me leave you with the part that is genuinely reassuring, because it is true and it belongs here. Human beings are extraordinarily good at this. Lighthouse keepers, submarine crews, polar winterers, sailors on long voyages, before radio existed at all. For most of human history, most people lived without any realistic prospect of rescue from anything. And they lived well, and they were not consumed by it. The assumption of rescue is quite a recent luxury. The people who go will know exactly what they are accepting. That knowledge freely held, is a very different thing from danger imposed on someone who did not choose it. Let that room be quiet now. In the version we imagined, the crew member is fine. Most of them would be, most of the time, which leaves the largest question of the whole property. And we have been carefully avoiding it all night. All of this assumes there is something to breathe inside the sealed volume, and that the air and the water and the waste keep cycling through each other correctly, month after month, without ever being resupplied. We have tried that on Earth, under glass, in the Arizona desert, with unlimited outside help available. It did not go the way anyone expected. There is a building in the Arizona desert, about an hour north of Tucson, near a small town called Oracle, and I think about it more than almost anything else in this subject. It is still there. You can visit it. From outside it looks like something from a World's Fair. A sprawl of white steel frames and glass, stepped pyramids, and a great dome, sitting in scrubland at the foot of the Santa Catalina Mountains. Just over 3 acres under sealed glass, around 6,500 windows, 91 feet at its highest point, roughly 200,000 cubic meters of enclosed volume. It was called Biosphere Two, on the reasoning that the Earth itself is Biosphere One. Before I tell you what happened inside, one piece of honesty about where it sits in the field, because the popular telling usually gets this wrong in both directions. Biosphere 2 was not the only attempt at a closed ecological system, and it would be misleading to say so. The Soviet Union ran a program called Biosphere 3 in Krasnoyarsk from the early 1970s, sealing small crews inside for months at a time, with algae and crop chambers regenerating their air. NASA ran a long series of studies under the heading of Controlled Ecological Life Support Systems. China has operated a facility called Lunar Palace 1, with crews inside for a year at a stretch. There is a real and continuing research field here, and much of it has produced quietly useful results. What makes Biosphere 2 singular is its scale and its ambition. Nobody before or since has attempted to seal 8 people inside a complex, multi-biome, nearly self-contained ecosystem for 2 years. That is why it matters. And that is why the failure taught more than most successes do. This one is a story rather than a list of numbers. So let it be told at story speed. The project was privately funded, largely by a Texas businessman named Ed Bass, and construction ran from 1987 through 1991. Inside that sealed glass, the designers built 5 wild biomes: a rainforest, a savanna, a fog desert, a mangrove wetland, and an ocean, a genuine one, close to 1 million gallons of salt water with a coral reef in it and a wave machine to keep the water moving. Alongside the wild areas, there was a farm of about half an acre where the crew would grow their own food, and living quarters, and beneath it all, a technical basement full of machinery that the project called the Technosphere. On the morning of the 26th of September, 1991, 8 people walked in, 4 men and 4 women. The airlock closed behind them, and a welded stainless steel liner beneath the whole structure, and 6,500 sealed panes above it separated them from the rest of the world. The plan was 2 years. Grow all their own food. Breathe air regenerated entirely by the plants inside. Recycle all their water. Take nothing in. And the ceiling was serious. This was not a building with a closed door. It was engineered to a standard of air tightness far beyond ordinary construction. And it included two enormous flexible chambers, the project called lungs, great domed diaphragms that could expand and contract. Because a sealed glass building in the Arizona desert heats during the day and the air inside expands. And without somewhere for that pressure to go, the glass would simply fail. Think about that detail for a moment. They had to build breathing lungs into the architecture itself, just to survive the difference between afternoon and night. For the first months, things were difficult in the ordinary way. Food was tight. The farm produced less than projected, in part because of unusually cloudy weather in that first year. And the crew spent an enormous fraction of their waking hours on agriculture. They lost weight, most of them substantially. A physician on the crew, Roy Wolford, who had a long-standing research interest in caloric restriction, monitored them. And the medical data from that period remains genuinely interesting. Wolford is also the source of the best description anyone has given of the place. He called it the Garden of Eden on top of an aircraft carrier. Hunger was expected, more or less. What happened next was not. The oxygen began to fall. Ordinary air is about 20.9% oxygen. That figure is one of the most stable things in your life. It is the same in this room, as in a forest, as on a boat. And it does not change. Inside Biosphere 2, over 16 months, it slid down to around 14%. Let me translate. 14% oxygen at sea level is roughly equivalent to the air on a mountain around 4,000 meters up. The crew were living at altitude without having climbed anything. They reported exhaustion, breathlessness on stairs, difficulty concentrating, sleep problems, including sleep apnea. One crew member was later described as being unable to complete simple arithmetic. They were, in a real medical sense, becoming hypoxic. Slowly, in a building on flat ground in Arizona. In January of 1993, the project made a decision. They pumped oxygen in from outside. That is where the story usually stops. With a sneer, the sealed world was not sealed. The experiment failed. But hold on, because the interesting part has not happened yet. Nobody knew where the oxygen had gone. That is the fact I want you to hold above every number in this chapter. 8 extremely motivated people, an enormous budget, a team of consulting scientists, and a building full of instruments. And they could not account for the missing oxygen. The obvious explanation was that it was being consumed by respiration. The crew, the plants at night, and above all, the soil, which had been made deliberately rich in organic material to support agriculture. Soil microbes consume oxygen and release carbon dioxide. That much was clear. But if that were the whole story, the carbon dioxide should have risen to match, and it had not. The carbon dioxide levels did not account for the missing oxygen. Something was taking it out of the system and not giving anything back. The answer was eventually found, and it was published in Science in 1996 by Jeff Severinghaus and colleagues, with Wallace Broecker of Columbia University among the authors. The analysis pointed to the concrete. The building contained a very large quantity of exposed concrete, and concrete cures slowly, absorbing carbon dioxide from the air and locking it chemically into the material as calcium carbonate. So the soil microbes were consuming oxygen and producing carbon dioxide exactly as expected. And the concrete was quietly absorbing that carbon dioxide and hiding the evidence. The oxygen was going into the soil. The carbon was going into the walls. Let that sit, because it is one of the most instructive facts in this entire survey. The system was not defeated by something exotic. It was not a failure of biology or of ambition. It was defeated by the building material, by an ordinary chemical process happening in ordinary concrete in a building on Earth, with a team of scientists monitoring it. And it took years and isotopic analysis to work out what had happened. Nobody put that in the model, because nobody thought of it. Here is the lesson stated once, plainly, and then we can move on. In a closed habitat, the building is not a container around the experiment. The building is part of the experiment. There is a second half to the story that is less well known and equally important. Inside those beautifully designed biomes, the ecology did not behave. Most of the pollinating insects died out, which is a serious matter where you are trying to grow food. Populations of certain ants and cockroaches exploded. Morning glory vines, introduced deliberately, ran wild and had to be fought back constantly. The ocean chemistry drifted. A substantial fraction of the vertebrate species introduced did not survive inside the glass. And it was noticed that many of the trees grew fast and weak, because without wind there was no mechanical stress signal telling them to develop the reinforcing wood that keeps a trunk standing. Some of them fell over. Every one of those failures is a version of the same lesson. The designers built a system out of components they understood individually, and the interactions between those components produced behavior nobody predicted. The first crew completed their 2 years and walked out on the 26th of September, 1993. A second closure began in March of 1994 with a crew of 7 and ended early, amid management disputes that became genuinely acrimonious and are not really our subject tonight. The building was later run by Columbia University and is now operated by the University of Arizona as a research facility, which I think is the right ending for it. It is still producing science. Now, where does this sit? What happened inside is measured. The oxygen decline, the concrete mechanism, the species losses, the agricultural shortfall, all documented and published in the peer-reviewed literature. The interpretation is where people disagree, and I want to give the fair version of both sides. The critical reading is that this was an over-ambitious project with serious design flaws, run outside conventional research institutions, and that a properly engineered life support system would look nothing like it. That reading has real force. Biosphere 2 tried to be a miniature Earth, with wild biomes and an ocean, which no Mars habitat would attempt. A real system would be mechanical and controlled, not ecological and self-organizing. The environmental control and life support system aboard the International Space Station is exactly that. And it works. And it has kept people alive continuously for a quarter of a century. The sympathetic reading, which is mine, is that this misses what the experiment actually demonstrated. Biosphere 2 was not primarily a test of whether a particular design works. It was a test of whether we can predict how a closed system will behave. And the answer was no. Not because the people were foolish, but because closed systems generate surprises from the interaction of parts, and the number of possible interactions grows far faster than anyone's ability to enumerate them. Now the connection to Mars, And 2 facts about the comparison that are usually left out. The first is scale. Biosphere 2, enclosed around 200,000 cubic meters for 8 people, with an ocean and a rainforest. Thousands of tons of soil and water and living biomass acting as a buffer against change. A Mars habitat would have a tiny fraction of that volume and almost none of that buffering. Small systems drift faster. There is less inertia to absorb a mistake. The second is help. When the oxygen fell in Arizona, the answer was to open a valve and let some in from the largest oxygen reservoir in the solar system, which was sitting directly outside the glass. On Mars, outside the glass, there is a thin skin of carbon dioxide. There is no valve. And one more thing, marked as my own reading, because it is why I placed this chapter where I did. The station works. And I said that honestly a moment ago. But look at how it works. It is resupplied constantly. Cargo vehicles arrive several times a year carrying water, oxygen, filters, spare parts, and food. Its water recovery is genuinely impressive and improving. And the remainder is delivered by rocket. A Mars settlement across a 500-day surface stay cannot be resupplied on any useful timescale. So, the honest state of the art is this. We have several partial closed system experiments, some of them genuinely successful within their limits, and one uniquely large attempt to put 8 people inside a complex, nearly self-contained ecosystem for 2 years. That attempt lost a quarter of its oxygen to its own walls, and nobody noticed until people started struggling to climb stairs. That is not a verdict of impossible. It is a note that the property's most critical system has been tested once at that scale, with outside help available, and did not hold. The building in Arizona is standing there tonight, quiet and half empty, doing useful science under a desert sky. Let that be enough. Because there is a question I have been putting off all evening, and it is the one that every single person listening has probably already asked themselves. What would they actually eat? Here is a number that reframes the whole problem. A human being needs somewhere around 800 grams of food per day, dry weight, to stay properly fed and functional. Multiply that by 6 people, and by the roughly 1,000 days of a full mission, and you get something in the region of 5 metric tons of food. That is before packaging. That is before the water it takes to rehydrate any of it. Now remember, Chapter 4. The heaviest thing ever landed on Mars weighed 1 ton. That is the whole chapter in one comparison, and everything else follows from trying to escape it. Nothing here needs deciding. It is a problem about groceries, and groceries are gentle company at this hour. There are only 2 ways out of that arithmetic. Carry it, or grow it. Every serious plan is some mixture of the 2, and both halves have real problems. Start with carrying it, because that is what we currently do. Everything eaten in orbit is brought from Earth, and the food system aboard the International Space Station is genuinely sophisticated. Thermostabilized pouches, rehydratable meals, irradiated meats, a standard menu running to hundreds of items. Developed by food scientists who take the work seriously because morale in a confined space runs partly through the galley. But station food has a shelf life measured in a year or 2, and it is resupplied constantly. A Mars mission cannot be resupplied, which means food packed before launch has to remain safe and nutritious for the entire mission. And because cargo is usually sent ahead on an earlier transfer window, some of it may need to sit on that surface for years before anyone opens it. And here is the quiet problem. Food does not simply stay the same in a sealed pouch. Some vitamins degrade with time, with heat, and with the sterilization processing that makes long storage possible in the first place. Vitamin C is the famous one. Certain B vitamins and vitamin A also decline. NASA has studied this specifically because it is a genuine mission planning constraint. And the requirement of a 5-year shelf life for a Mars-class mission is not currently met by every item on the menu. Sit with what that implies. It is possible to build a food supply that keeps people alive and slowly starves them of specific micronutrients. On a timescale where the deficiency shows up 2 years in, 400 million kilometers from a pharmacy, vitamin supplements are the obvious answer, and they degrade too. This is not a catastrophe. It is a solvable engineering and nutrition problem, and people are working on it. But it is a real one, and it is invisible in every rendering of a Mars base ever drawn. Now, the other option, grow it. This is where it gets interesting, and where there is genuinely good news. Plants have been grown in space for decades, in Soviet and Russian facilities, and later aboard the station. The current system is called Veggie, a small plant growth chamber about the size of a piece of carry-on luggage, using red and blue light, emitting diodes and pillows of growth medium. In August of 2015, astronauts aboard the station ate red romaine lettuce they had grown themselves. They tasted it on camera, and their faces were the faces of people eating a salad, which is not an expression anyone had ever worn in orbit before. Since then, the list has grown. Different lettuces, Mizuna mustard, Chinese cabbage, radishes, and in 2016, zinnias, which were not food, but which mattered enormously, because the crew reported that tending flowers was good for them in a way that was hard to quantify and impossible to dismiss. That last point deserves a moment. On a 500-day surface stay, a greenhouse is not only a food source, it is the only green thing, the only living thing that is not a person, the only place where something grows and changes and needs you. Every psychologist who has looked at long-duration isolation has said something about this. It may turn out that the garden matters more for the mind than for the stomach. So plants grow in space. Excellent. Now the harder version. Can you grow food on Mars using Martian materials? The soil is the first problem, and we already know why. Perchlorate. Martian regolith is not soil in any agricultural sense. It has no organic content, no soil biology, no nitrogen in usable form, and it contains perchlorate at levels that are toxic to many plants and, more importantly, toxic to the people who would eat those plants if the compound accumulates in the tissue. There is real research on this. Studies using Mars regolith simulant, meaning terrestrial material formulated to match the measured chemistry, have grown crops with mixed success, generally requiring the addition of organic material, and there is genuine work on perchlorate removal, both by washing and by using bacteria that metabolize the compound. Which brings us back to the point from Chapter 8 that a hazard and a resource are often the same substance seen from two angles. But washing perchlorate out of soil requires water, and we are about to spend an entire chapter on how expensive water is over there, which is why most serious plans skip the soil entirely and go hydroponic. No dirt. Roots in a nutrient solution, under artificial light, in a controlled chamber. That solves the chemistry. It creates a different problem, and it is the one that governs everything. Light. A plant is a machine for turning light into food, and on Mars the light is dimmer. As we saw standing out there, roughly 43% of what falls here. Less after dust. So either you build enormous, transparent, growing areas on the surface, which brings back every radiation problem from Chapter 7, or you grow under electric light, which means the food supply becomes a line item in the power budget. And the power budget already has the oxygen plant on it, and the water extraction, and the heating, and everything else. Estimates of the growing area required to feed one person vary enormously with the assumptions, but the figures in the literature tend to run to something in the region of 50 square meters per person for a full diet, and that is with efficient crops under optimized conditions. For a crew of 6, that is a substantial indoor farm, pressurized, lit, heated, watered, and maintained. All of it landed or built. So let me place this whole chapter. The nutritional requirements are measured. Human dietary needs are among the best characterized things in all of medicine. Growing plants in microgravity is measured and demonstrated. Veggie works. People have eaten the results. Growing enough food to sustain a crew, en masse, using local resources, at the required scale, has never been done by anyone. There is no facility anywhere on Earth that has fed a crew of 6 entirely from a closed loop for 500 days without resupply. Biosphere 2 came closest and, as we just discussed, they were hungry the whole time and the oxygen was falling. That line remains blank. And now let me tell you what this chapter is actually about. Because it is not really about calories. It is about how many things have to work at once. Consider what has to be true for one meal on Mars. The power system has to be running, because the lights depend on it. The water system has to be running, because the plants drink. The atmosphere in the growth chamber has to be maintained, at the right pressure and the right carbon dioxide concentration. The temperature has to hold. Nothing can have gotten into the chamber. No mold. No pest. Nothing. The nutrient chemistry has to be correct. And somebody has to have done all the daily work of tending, which in Biosphere 2 consumed an enormous share of the crew's waking hours. Miss any one of those for long enough and the crop fails. And the next crop is a growing season away. And the emergency reserve is whatever was packed on Earth 2 years earlier. On this planet, food is what happens when you do nothing. Fruit falls off trees. Grass grows. The entire biosphere produces edible material continuously, whether anyone is paying attention or not, and has done for hundreds of millions of years. There, dinner is an achievement of engineering, repeated every single day, forever, which is a strange thought to hold while lying in a house that almost certainly has food in it right now, sitting quietly in a cupboard, requiring nothing from anyone. The same is true of the air in that room, and it is time we looked at how you would make some. This is the good news chapter. You can loosen your hold for it. Let me put you in a room. It is the 20th of April, 2021, 2 months after Perseverance landed, somewhere at the Jet Propulsion Laboratory in Pasadena, and in offices at the Massachusetts Institute of Technology. A group of people are watching telemetry come in from a device they have been building for the better part of a decade. Michael Hecht has been the principal investigator for most of that time. It is the same Michael Hecht from Chapter 8, the one whose instrument found perchlorate in the soil at the Phoenix landing site 13 years earlier. Some people spend a whole career asking one planet a series of increasingly specific questions. The device is called MOXIE, which stands for the Mars Oxygen In Situ Resource Utilization Experiment. It is about the size of a car battery, weighs roughly 17 kilograms, and it is bolted inside the body of the rover. What it is doing right now in Jezero crater is this. It draws in the Martian atmosphere, which, as we established, is about 95% carbon dioxide. It compresses it. It heats it to around 800 degrees Celsius, and it passes it through a ceramic electrolysis cell where the carbon dioxide molecules are split apart. Carbon monoxide out one side, pure oxygen out the other. The numbers come back across a gap that takes minutes to cross. About 5 grams of oxygen, roughly 10 minutes of breathing for one person. I want to sit with this, because I have spent 12 chapters being carefully skeptical, and this deserves the opposite treatment. That was the first time a machine produced oxygen from the resources of another planet. I want to be exact about the claim, because the sloppy version gets said a lot, and it is not true. Spacecraft have made oxygen off Earth for years. The station splits water into hydrogen and oxygen continuously, and has done for a long time. But that water came from Earth. It was carried up. What happened in April of 2021 was different in kind. The raw material was already there. It had been sitting in that atmosphere for billions of years. And a machine took some of it and made something a human could breathe. NASA compared it to a small tree on another world. That is a fair description, and the people who built it deserve to have it said plainly. The device ran 16 times over the following 2 years, in different seasons, at different times of day, under different atmospheric conditions, deliberately, to prove it could work across the range of environments Mars actually presents. It ran during a dust storm. It ran at night. By the time the experiment concluded in the summer of 2023, NASA reported a total production of about 122 grams of oxygen, with a best rate around 12 grams per hour and a purity above 98%. That is the good news. And it is real, measured, demonstrated, published, repeated 16 times on the surface of another planet. Now the arithmetic, which is the point of this chapter, and is not a criticism of anyone. A human being consumes something in the region of 800 grams of oxygen per day, call it 33 grams an hour, roughly, though it varies enormously with activity. The device at full rate produced 12 grams an hour. So the most successful oxygen production system ever operated on another world produces, at its best, about a third of what one person needs to keep breathing. Total lifetime output across 2 years and 16 runs was 122 grams. That is under 4 hours of breathing for a single individual. I want to be very careful how this lands, because it would be easy to present that number as a debunking, and it is nothing of the kind. It was never intended to supply anyone. It was a technology demonstration, and its entire purpose was to prove that the chemistry and the hardware function in the real Martian environment, rather than in a laboratory chamber. It succeeded completely at what it was for. The question is, what happens next? And here the scale is daunting. The consensus in the mission architecture literature is that the largest oxygen requirement is not breathing at all. It is propellant. To lift a crewed ascent vehicle off the surface and back toward Earth, you need an enormous quantity of oxidizer. And the figures appearing in NASA study documents run into the tens of tons. The project's own descriptions have pointed at a target scale in the region of 2 to 3 kilograms per hour for a full system, running continuously for months or years ahead of the crew's arrival. 2 to 3 kilograms an hour against 12 grams an hour demonstrated, a factor of roughly 200. Let me be clear about where that sits, because this is a place where honesty cuts in a useful direction. The chemistry is measured. Solid oxide electrolysis works. En masse. In real conditions. That is settled. The scale-up is an open engineering question, and genuinely so. There is no physical barrier. This is not like the radiation shielding problem where the physics itself resists you. The main constraints are electrical power, thermal management, the durability of ceramic cells across thousands of hours of high-temperature cycling, and the mass of equipment you have to land. Power is the quiet constraint underneath all of it, and you will have noticed it turning up in every chapter now. The greenhouse needs it. The water extraction needs it. The oxygen plant needs it. Solar delivers less than half its terrestrial intensity there, and dust storms can dim the sky for weeks, which is why most serious architectures for surface power include nuclear fission, and why NASA and the Department of Energy have been testing a small reactor concept called kilopower, with a demonstration that ran successfully in Nevada in 2018. So the picture is not discouraging. It is a picture of a demonstrated principle waiting on a great deal of infrastructure. But here is what I actually want you to take from this chapter, and it is a shift in perspective rather than a number. Notice what that little box reveals about the nature of that place. On Earth, oxygen is not manufactured, it is simply present, as a byproduct of photosynthesis running continuously across the entire planet for more than 2 billion years. The oxygen in your lungs at this moment was released by a plant or an alga, quite possibly by phytoplankton in an ocean you have never seen, and it arrived at your window through nothing more than the ordinary circulation of the atmosphere. Nobody built the machine. Nobody maintains it. There is no failure mode that requires a technician. On Mars, oxygen becomes a product. It has a production rate, a power budget, a maintenance schedule, and a failure mode. It becomes something that can stop. And once you see that, you see it applying to everything. Water becomes a product. Heat becomes a product. Food becomes a product. Pressure becomes a product. Every single condition that this planet supplies to you for free, continuously, without asking, has to be manufactured over there by machines that people built and that people must keep running. That is the deepest change of all. And it is not really a technical one. It is a change in the relationship between a person and the place they live. Here, the world holds you up. There, you hold the world up. Every day. Forever. with no day off. Which brings us to the substance. All of this depends on more than any other. There is water on Mars. That sentence is true. It has been confirmed by multiple spacecraft from multiple countries across more than 20 years, and it is one of the great findings of modern planetary science. It is also one of the most misleading true sentences in this entire subject, and I want to take it apart gently, because the way it is usually presented does real damage to people's understanding of what that place is. This is a practical problem, and practical problems are restful in their way. Nothing here requires anything from anyone tonight. Start with what we genuinely know, because the knowing is beautiful and deserves to be said properly. Begin at the poles. Both carry permanent ice caps, and both are visible from Earth through a decent telescope, which means people have been looking at them since the 17th century without understanding what they were. The northern cap in particular is mostly water ice, a genuine sheet of it, kilometers thick in places, and the volume is substantial. Now leave the poles, because the poles are not where anyone would live. Temperatures there are extreme, even by Martian standards, and the sunlight for power is poor. The more important discovery came in 2002, when NASA's Mars Odyssey orbiter, using an instrument that detects neutrons emerging from the surface, found the signature of large amounts of hydrogen in the upper meter of soil across enormous regions of the planet, particularly at middle and high latitudes. Hydrogen, in that context, almost certainly means water, locked in ice. Then, in 2008, the Phoenix lander did something quietly magnificent. Its robotic arm scraped a shallow trench in the northern plains, and the camera photographed bright material at the bottom. Over the following days, that bright material vanished. It had sublimated, turning directly from ice to vapor in the thin air, which is exactly what water ice does at that pressure, and exactly what a salt or mineral deposit would not do. That was ice, photographed, in the ground, disappearing on schedule. It is one of my favorite pieces of evidence in all of planetary science, because it is so simple. Dig a hole, take a picture, take another picture, watch it go. Since then, orbital radar, particularly the instruments aboard Mars Express and the Mars Reconnaissance Orbiter, has mapped what appear to be substantial buried ice deposits at many locations, including some at lower latitudes where a settlement might plausibly be placed. There is a NASA-led effort called subsurface water ice mapping, working exactly this problem, precisely because where the accessible ice is determines where anyone could go. So the finding is real, it is solid, and it is genuinely encouraging. Now, what that sentence quietly leaves out: the water on Mars is not water, it is ice, mixed into frozen ground, at temperatures far below anything on this planet, under a surface often covered by a layer of dry dust and rock, on a world where you cannot go outside without a suit, and where every machine you use had to be flown across the solar system. Consider what has to happen to turn that into something a person can drink. You have to find it, which means surveying and probably drilling test holes. You have to reach it, which means excavation, and excavation at 38%. Gravity is harder than it sounds, because digging machines work by pressing down, and your machine weighs about a third of what it would here. So you need to anchor it or make it much heavier. You have to break frozen ground that at -60 degrees behaves less like soil and more like concrete. You have to move that material. You have to heat it enough to release the water, which costs energy. And there is no cheap heat anywhere on that planet. You have to capture the vapor before it escapes into an atmosphere that will not hold it. You have to purify it, because it will contain perchlorates and other salts. And you have to do all of this with equipment that cannot be repaired by anyone who is not already there. Every one of those steps costs power. And you know by now what power is on Mars. So the accurate version of the sentence is not that there is water on Mars, it is that there is a raw material on Mars from which water can be manufactured, at significant and continuous energy cost, by machines that must be landed within the mass budget we discussed in Chapter 4. That is a completely different proposition, and it is still a good one. It is enormously better than having to carry every liter from Earth, which would be flatly impossible. Local resources are the only reason any of this is conceivable at all. I am not knocking down the finding. I am placing it correctly. There is a second source worth mentioning, and it comes with an instructive twist. In 2015, NASA announced findings about dark streaks that appear on certain Martian slopes during warmer seasons and fade again afterward. They are called recurring slope lineae, and the announcement reported spectral evidence of hydrated salts associated with them, which was widely reported as evidence of flowing liquid water. Since that announcement, the interpretation has become genuinely contested. Later work has suggested that at least some of these features may be dry granular flows, essentially sand and dust avalanching down slopes, with the hydrated salt signature explained in other ways. As of the time this was written, this remains an open question in the literature rather than a settled one. I am telling you about it not because it changes the picture much, but because it is a clean example of the thing I promised at the beginning. A finding was announced. It was exciting. It was reported everywhere. And then careful people spent years testing it, and the picture became more complicated rather than less. That is not a scandal. That is the process working. It is one of the few human activities where being shown to be wrong is treated as a service rather than a defeat. And even in the version where liquid brines do exist, they would be extremely salty, extremely cold, and almost certainly loaded with perchlorate, not a stream, a chemically hostile film in the top layer of soil. Now, the number that reframes this chapter: a person needs a few liters of water a day for drinking. Add hygiene, food preparation, and the basic functioning of a habitat, and figures used in mission planning run considerably higher. Add the greenhouse from the last chapter, and the number climbs sharply again. Because growing food is water intensive, even in the most efficient hydroponic systems. The International Space Station addresses this with recycling, and its water recovery systems are impressive. NASA reported in 2023 that the station had achieved around 98% water recovery, involving reclamation of moisture from the air, from urine, and from every other available source. But notice the direction that number points. 98% recovery means 2% loss. On a station resupplied several times a year, 2% is trivially replaced. En masse, that 2% has to be manufactured out of frozen ground, continuously, forever. So the water system on Mars is not really a water system. It is a recycling system with a mining operation attached to cover the losses. And both have to run without interruption. The ice is measured, Odyssey, Phoenix, orbital radar, ongoing mapping. The extraction technology is an open engineering question. Concepts exist, some of them clever, including approaches that heat the ground in place and capture the vapor without excavating at all. None has been demonstrated at scale on Mars. And there is a blank line hiding in here that I want to name. No one has ever operated a continuous industrial process on the surface of another world. Not once. Everything we have ever done off Earth has been observation, sampling, and short demonstrations. The oxygen box ran 16 times for a few hours each. That is the record. There has never been a machine anywhere beyond Earth that had to run continuously for years, in dust, at extreme temperature swings, with maintenance performed by people wearing pressure suits. The entire concept of a Mars settlement depends on that being possible. It has never been tried by anyone. Notice the pattern that has been building all night. Each chapter finds that the resource exists and that the process to use it exists in principle, and that the demonstration at the required scale does not exist yet. That is not a wall. It is a very long staircase, and the top of it is not visible from here. We have now surveyed the whole physical property: road, radiation, landing, air, surface, shelter, dust, body, medicine, life support, food, oxygen, water. What remains is the part almost every survey forgets, and it has ended more expeditions in history than weather or supplies ever did. Let me describe a moment that will happen. If any of this happens, and that almost nobody talks about, somewhere in the first weeks of the crossing, someone aboard that vehicle looks out at Earth. For the first days it is enormous, filling a window, the way it does for everyone who has ever been to orbit. Continents move past. Weather systems turn. It is unmistakably the place where everything has ever happened. Then it is a disk. Then it is a bright blue point. Still, obviously, a world. Still holding its color. And then, at some point during that 6 to 9 month journey, it becomes a star. Not gone. Still there. Still findable. Still among the brightest things in that part of the sky. But no longer a place. A point of light among other points of light. And if you did not know which one it was, you could not pick it out. Remember what we saw standing in that crater. From the surface of Mars, Earth is an evening star with a fainter companion beside it. That is the destination's view. But this happens earlier. In transit. In stages. Over weeks. While a person watches it happen. Every human being who has ever lived has done so with that planet underneath them or hugely present beside them. The furthest anyone has ever been is the far side of the moon, and even those crews could hold up a thumb and cover the Earth, but could still see it as a world, with weather on it, and they were back within days. The people on that vehicle will be the first to watch it become a star. Let your hands open. There is nothing sad in this. It is simply new. And new things are worth noticing. Psychologists have discussed this for decades, precisely because nobody has experienced it. Every instance of homesickness in the history of our species has occurred with home present. Somewhere on the same sphere. You could walk toward it. In principle, Even if the walk was impossible, the direction existed. Nobody knows what it does to a person to have home be an object in the sky. That line is blank, and it is worth pausing on the strangeness of it. We have an enormous literature on human separation, grief, longing, and isolation. All of it was written on one planet, by people who never left it. Now let me give you the evidence we do have, because I do not want to trade in atmosphere when there is real research available. There is a substantial body of work on human beings in prolonged isolation and confinement, from 3 main sources. The first is Antarctica, research stations there, particularly Concordia and the Amundsen-Scott South Pole Station, are inaccessible for months during the austral winter. Small crews, no departure possible, extreme environment outside, continuous darkness for a good part of it. The European Space Agency has treated Concordia explicitly as a spaceflight analogue for years. The second is spaceflight itself. Decades of station experience, with careful psychological monitoring. The third is deliberate simulation. And the most ambitious was a Russian-led project called Mars 500, run in Moscow by the Institute of Biomedical Problems. Its main phase sealed 6 men into a mock spacecraft on the 3rd of June, 2010, and did not open the hatch until the 4th of November, 2011, 520 days, in a facility of about 550 cubic meters, with communication delays imposed of up to 20 minutes each way. 3 Russians, a Frenchman, an Italian Colombian, and a Chinese crew member. The findings are worth knowing, and one is genuinely striking. A paper published in the Proceedings of the National Academy of Sciences in 2013, with Matthias Basner of the University of Pennsylvania as lead author, reported on the crew's sleep and activity across the whole period. Most of the crew showed disturbances in sleep and in their daily rhythms. One crew member developed a persistent sleep pattern that drifted away from the 24-hour schedule the mission was running on, which meant that for parts of the mission he was awake while the others slept. Think what that means in a sealed volume with 5 other people. Not conflict, just a quiet desynchronization. One person living slightly out of phase with everyone else for months. The same body of research reported that the crew's overall activity declined across the mission. They moved less, engaged less, and spent more time in a kind of behavioral quiet as the months accumulated. Researchers have discussed this as hypokinesis and withdrawal, and it appears in the Antarctic literature too. Now I have to be careful, and I want to do it properly, because there is an easy and dishonest move available here. The easy move is to say that a simulation in Moscow must understate the difficulty because the crew knew they were safe, and therefore the real thing would be worse. That is only half true, and I am not going to sell you the half. Yes, the simulation omitted the genuine dangers. No radiation, no microgravity, no vacuum outside, no possibility of dying because a seal failed. The crew knew that beyond the hull was a car park in Russia, and that a real emergency would result in the hatch being opened. But the simulation also omitted things that might have helped enormously. There was no purpose. Nobody was going anywhere. The mock Mars landing was a room with a sand floor. There was no arrival, no genuine discovery, no view out of a window at a world nobody had ever stood on, no scientific work whose results anyone was waiting for. There was no novelty of any kind after the first weeks. And there was the peculiar psychological weight of knowing you are a research subject being watched. A real crew would have all the terror the simulation lacked. They would also have the most extraordinary experience any human being has ever had. Arriving somewhere new, doing work that matters, watching that golden sky through a real visor. Which of those dominates? Nobody knows. The simulation differs from the real thing in both directions at once, and it therefore cannot tell us whether the total psychological burden of a real mission would be greater or smaller than what those 6 men experienced. That is the honest reading. It is less satisfying than the dramatic one, and it is what the evidence supports. Now, 2 more features that have no analogue anywhere. The first is the absence of an exit. In Antarctica, the winter ends. The date is on the calendar. Every person overwintering knows precisely when the aircraft can come, and that knowledge is load-bearing. On Mars, the date exists too, which genuinely helps, but it is measured in years, and it is not adjustable by any effort or emergency. The second is the shape of contact with home. You can send messages, long and thoughtful ones, and receive them back hours later. That is not nothing, and it is far better than the letters that sustained sailors for centuries. But a conversation is a specific thing. It has turn-taking, and interruption, and repair, and the small, immediate feedback that tells you the other person is following. Every relationship you have is maintained partly through that mechanism, and it will not be available. There is no conversation available. There is only correspondence. Let me end this chapter on the honest other side, because a survey that only lists defects is not a survey. Human beings are astonishingly good at this. Every Antarctic winter crew comes out. Most of them go back. Submarine crews complete patrol after patrol. The station has been continuously occupied for a quarter of a century by people from countries that have been in serious political conflict throughout. And it has worked. Every single day. Because the people aboard decided it would. And Mars 500 ended on schedule. 6 men walked out under their own power after 520 days. And the mission was reported to have finished with the participants in good physical and psychological condition. Nobody quit. Nothing had to be stopped. We are a species that has always sent small groups of people into places where nobody could help them. And those people have generally coped better than the people at home expected them to. So this is not a chapter about frailty. It is about a set of conditions we have never combined before, and the reasonable expectation that human beings would probably manage them, probably, with one exception, because everything so far concerns adults who chose this, who were screened and trained, and who understood what they were accepting. A settlement is not a mission. A settlement, by definition, is a place where people stay. And a place where people stay is eventually a place where people are born. And that is the one question in this entire survey where the data is not thin or contested or preliminary. It does not exist at all. I want to handle this chapter carefully, and I want to tell you in advance how, so that you can relax into it rather than brace against it. This subject gets sensationalized more than any other in this field. There are videos about it that reach for horror, that describe outcomes nobody has observed, that treat an open scientific question as though it were a known catastrophe. I am not going to do that. And there is no need to, because the actual situation is more interesting than the invented version. What follows is a description of an empty space in human knowledge. Nothing more, and nothing less. There is nothing frightening here, only something missing. Let me begin with the reason the question exists at all. A mission and a settlement are different things. And the difference is not size or duration. It is our intent. A mission goes and returns. Everyone aboard is an adult. Screened, trained, volunteering, and going home. Whatever risks they accept for themselves and for a bounded period. That is the Apollo model and the station model, and it is the model of every human spaceflight that has ever occurred. A settlement is something else. A settlement is a place where people stay, and the word for a place where people stay across generations is not a base. It is a community, and every community in the history of our species has had, at its center, the arrival of new people who were born there. You cannot have a permanent human presence without births. Not eventually, not as a philosophical nicety, as a matter of arithmetic. A population that does not reproduce is not a settlement. It is a rotating staff, permanently dependent on Earth for every single one of its members. Forever. So if the goal is a base, this chapter does not apply. If the goal is anything that could honestly be called a second home for humanity, this chapter is the foundation of the entire building. Here is the state of knowledge. No mammal has ever completed all three stages: conception and gestation and birth, in a gravitational environment other than Earth's. I say all three deliberately, because pieces of the process have been attempted, and it would be misleading to imply otherwise. There have been reproductive experiments in orbit with various organisms going back decades. Japanese researchers flew Medaka fish aboard a shuttle mission in the 1990s, and those fish mated in orbit and produced offspring that hatched there, which was a genuine milestone. Amphibian eggs have been fertilized and developed in microgravity. Insects have bred. Plant reproduction has been studied extensively. And Arabidopsis has been grown through multiple generations aboard the station. Mammals are a different matter. Pregnant rats have flown, and Soviet and later Russian missions carried rodents on Bion satellites. Some pregnancies flown in orbit did produce offspring after return to Earth, and researchers noted differences in the vestibular development and behavior of pups exposed to microgravity during gestation. There has been work on the effect of spaceflight on reproductive tissue. And in 2023, a Japanese team led by Teruhiko Wakayama reported successfully culturing mouse embryos aboard the station through early stages of development, which was widely and correctly described as a first. Every one of those is real science, and every one of them is a fragment. None is a mammal conceived in reduced gravity, carried to term in reduced gravity, born in reduced gravity, and raised to adulthood in reduced gravity. That has never been done with any mammal, anywhere, at any gravity level other than 1g, and that is before the second complication, which we discussed in Chapter 3 and which applies here with particular force. Radiation poses greater risk to rapidly dividing cells, and a developing embryo is essentially nothing but rapidly dividing cells. Whatever the radiation environment means for an adult skeleton, it is a different question for a fetus. And again, there is no data. Now, Let me explain why this matters more than it might first appear. Consider what a developing body actually does. A skeleton forms according to load. We discussed that in the context of adults, but it is far more true of development. Bone does not simply appear in the shape of a human skeleton. It is laid down and continuously remodeled in response to the forces applied to it. And a growing child's skeleton is exquisitely responsive to this. The way a spine develops its curves, the way weight-bearing joints form, the density and architecture of bone, all of it is a conversation between genetics and mechanical load. At 38% gravity, that conversation would be conducted at different volume. The same applies to the cardiovascular system, which forms in response to the demands of moving blood against a particular gravitational gradient, and to the vestibular system, the balance apparatus in the inner ear, which calibrates itself during development against a constant reference direction of down, and to muscular development, and to the timing of an infant learning to lift its head, then sit, then stand, then walk. We do not know what any of that produces at 0.38 g, and I want to be scrupulously fair, because the possibilities run in both directions and the pessimistic reading is not automatically correct. It is entirely possible that development at 38% gravity proceeds essentially normally. Human bodies are remarkably tolerant of variation, and there may be a threshold well below 1 g above which the relevant signals are adequate. Nobody can rule that out. It is also possible that a person raised at 38% gravity would develop into a healthy adult who is simply somewhat different. Taller, perhaps, with different bone architecture, entirely well, but not able to comfortably visit Earth. It is also possible that the effects are more serious. All three are open. Anyone who tells you confidently which one is correct is telling you something they do not know. Now, the thing that makes this different from every other gap we have surveyed, every previous blank line could, in principle, be filled by a volunteer. An adult can consent to unknown radiation risk. An adult can consent to 500 days at an untested gravity level. An adult can consent to isolation, to the absence of rescue, to the whole enterprise. That is what informed consent is for. And adults have been accepting extraordinary risks on their own behalf throughout the history of exploration. And I have no argument with any of that. Their bodies, their choice. A child cannot consent to being born. Whatever the conditions of that development turn out to be, the person who experiences them had no say. And if the outcome is that they cannot survive on the planet their entire species came from, they did not choose that either. I want to mark this clearly as an ethical observation rather than a scientific finding. Because it is one. Nothing in the physics says this is wrong. This is a question about consent, and reasonable people hold different views on it. And I am not going to pretend my view is a measurement. But I will say this much plainly. Every serious discussion of Mars settlement I have encountered treats this as an open question requiring resolution rather than as a solved matter. The people working on this are not cavalier about it. It comes up in the literature. It is discussed. It simply has not been answered. And the trap is the same one from Chapter 9, but sharper. The only way to obtain the data is to run the experiment. And in this case, running the experiment means a specific child, in a specific room, on a specific world, whose development is the data. There is a way out. and it is the same way out. A rotating facility, in orbit, producing partial gravity, in which mammals could be raised through multiple generations at 0.38 g, with careful observation, for as long as it takes. Rodent generations are short, and a few years of such a facility would produce enormous knowledge. It has been proposed repeatedly. It has never been built. So here we are, at the line that determines whether the word settlement is even the right word. And the report says the assessment has never been performed and no schedule exists for performing it. Let me set that down gently, because I do not want to leave you holding it. None of this is happening tonight. There are no children on Mars. There is nobody there at all. And there will not be for a long time. This is a question about a possible future, being examined by careful people in advance, which is exactly the right time to examine it. And there is something genuinely admirable in a species that stops before doing a thing and asks what it would mean for someone who does not exist yet. Let it rest there. It has waited a long time, and it will keep. Because there is a related question, and it follows immediately whenever anyone starts thinking about settlements rather than missions. If a community is going to persist, how many people does it actually take? And the strange answer is that it depends almost entirely on a screw. Let me put an object in your hand. It is an ordinary screw, steel, a few centimeters long, threaded, with a slotted head. There are probably several hundred of them in the room you are lying in, holding the furniture together. Inside, the light fitting, in the hinges of the door. It cost almost nothing. You could buy a box of 100 without thinking about it. Let the screw sit in your hand a moment, because we are going to spend this chapter trying to make one on Mars. And it is going to turn out to be the hardest thing in this entire survey. Start with the metal. To have steel, you need iron. And to have iron, you need ore. So somebody has to prospect. Somebody has to find a deposit, which means geological surveying, which means instruments and vehicles and fuel and time. Then somebody has to extract it, which means digging equipment, which means power. In an environment where every machine weighs a third of what it would here and therefore has trouble pressing down on anything, then the ore has to be crushed, which needs a crusher, which is a large steel machine with hardened steel jaws that wear out and must be replaced. Then it has to be smelted, which means a furnace running at temperatures well above 1,000 degrees. That furnace needs a lining of refractory material that will not melt, which is its own industry. It needs a reducing agent, usually carbon, to strip the oxygen off the iron. It needs an enormous and continuous supply of energy on a planet where you already know what energy costs. Now you have iron. To make useful steel, you need to control the carbon content precisely, which means measurement, which means instruments, which means electronics. Then the steel has to be formed. A screw is not cast. It is made on machine tools. You need something to draw the wire, something to cut it, something to form the head, and something to cut or roll the thread. Every one of those machines is itself made of specially hardened steel, machined to tolerances of a fraction of a millimeter, and every one of them has bearings. And those bearings need lubricant, and lubricant is a chemical industry, and each of those machines was made by other machines. Lathes are made using lathes. Precision is inherited. There is a chain of ancestry running back through the entire Industrial Revolution. And every link in it exists on Earth, and none of it exists on Mars. You also need someone who knows how to do all of this. Not one person. Dozens of specialties, each with years of training behind it. That is a screw. There is an old essay from 1958 by Leonard Read called I Pencil, which makes exactly this point about a pencil. The wood, the graphite, the metal ferrule, the rubber, the lacquer, the ships that carry the materials, the machines that shape each part. Read's conclusion was that no single person on Earth knows how to make a pencil from scratch. It is the coordinated work of an unthinkable number of people spread across the planet, and none of them knows the whole process. On Earth, that entire pyramid is invisible, and it is invisible because it is enormous. A Mars settlement has to decide, item be item, which parts of that pyramid to import and which to build. Import too much, and you are not a settlement. You are a very remote outpost, entirely dependent on shipments that arrive once every 2 years. Build too much, and the population required explodes. Because each industrial capability requires people who possess it, and equipment to enable it, and the equipment to make that equipment. This is what the estimates are actually arguing about, and it is why they diverge so wildly. Let me give you the numbers, and then show you why they disagree. The older version of the question came from population genetics, and it asks the smallest group that can persist without collapsing from inbreeding depression and the loss of genetic diversity through random drift. There is a rough rule of thumb in conservation biology, sometimes stated as 50 and 500. Roughly 50 individuals to avoid immediate inbreeding problems. Roughly 500 to retain long-term adaptive potential. It is a rule of thumb rather than a law, and it has been debated and refined for decades. Applied to a space colony. Various analyses have produced figures from a few dozen to a few thousand. And an important modern point deserves stating clearly. If you can transport frozen genetic material, which is trivially easy compared to transporting people, the genetic constraint largely dissolves. Diversity can be shipped. So the genetics turns out not to be the binding constraint, which is why the more interesting analyses ask about labor instead. The most cited attempt is a paper by Jean-Marc Salotti of the Bordeaux Institute of Technology, published in Scientific Reports in 2020. His approach was elegant. He asked how many hours of human work per year the colony requires to maintain everything it depends on, and how many hours each person can supply. His conclusion, under his assumptions, was that the minimum was around 110 people. That number got a great deal of attention, and I want to give it the treatment it deserves, rather than simply repeating it. 110 is remarkably small, and it is small for a specific reason. The model assumed a substantial degree of sharing and cooperation, and it made particular assumptions about which industrial capabilities the colony would need to possess itself and which it could do without or import. Other analyses have arrived at very different figures, running into the tens of thousands and beyond. And the disagreement is almost entirely about that last point, about the screw. Analyses that assume continued heavy imports from Earth produce small numbers. Analyses that require genuine industrial self-sufficiency produce very large ones. This is not a case of some scientists being wrong. Everyone involved is reasoning carefully from stated assumptions. And the assumptions are the disagreement. There is no experiment that settles it, because it depends on decisions nobody has made yet about what kind of settlement is being attempted. And there is a blank line here too, and it is a big one. No human community has ever been industrially self-sufficient in isolation, at any scale. In modern history, not one. Every place on Earth trades. Every remote research station is supplied. Even the most isolated communities on this planet import metal and tools and medicine. And always have. A fully self-sufficient technological community is not something we have examples of. It is something we have models of. Which brings me to the observation I actually want to leave you with. Every technical chapter tonight has assumed people to run it. The oxygen plant needs technicians. The water extraction needs an operating crew. The greenhouse needs constant tending. And Biosphere 2 showed exactly how many hours that consumes. The habitat needs maintenance. The power system needs specialists. The medical facility needs someone trained. And every one of those machines needs spare parts, which must be either shipped or manufactured. And each of those people needs to eat, and breathe, and be housed, and be looked after when sick, which requires more machines, which require more people. That is the actual shape of the settlement problem. It is not a technology problem at all. It is a closure problem. Does the system close? Or does each addition create more demand than it satisfies? On Earth, it closes spectacularly. It took 10,000 years and 8 billion people to make it close that well. Nobody knows what the minimum is. That is the honest answer. And the range of serious published estimates spans from around 100 people to more than 100,000, which is not a disagreement about detail. It is a disagreement about kind. You can put the screw down now. It is a very ordinary object, and it will still be holding your door together in the morning. One item remains, before we can name the thing this video is about, and it is the only chapter tonight with nothing to do with physics or biology. Because a settlement is not only machines and bodies, it is also an arrangement between people. And every arrangement between people eventually faces the same question, which is what happens when they disagree. Picture 3 rooms on the same day, the 27th of January, 1967. 1 room in London, 1 in Washington, 1 in Moscow. In each of them, a table, a set of pens, and a document being signed simultaneously by representatives of governments that at that moment were pointing nuclear weapons at each other. The document had a long, formal name. Everyone calls it the Outer Space Treaty. More than 100 countries are now parties to it, including all of the major spacefaring powers. This chapter is about paperwork and about people, and neither is dangerous. Let me tell you what it says, because 2 of its provisions sit underneath everything else in this survey. The first is in Article 1. Space is declared the province of all mankind, and exploration is to be carried out for the benefit of all countries. The second is in Article 2, and it is the extraordinary one. It states that outer space, including the moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. Read that carefully, because it is a strange and remarkable sentence. No country can own any part of Mars, not by claiming it, not by landing on it, not by living there, not by any other means, which is a phrase deliberately written to close the doors that lawyers would otherwise find. Think about how different that is from every previous expansion in human history. The entire pattern of exploration on this planet involved arriving somewhere and claiming it, planting something, drawing a line on a map, and defending it. In 1967, in the middle of a Cold War between two powers racing each other to the moon, those same powers sat down and agreed in advance that this time nobody gets to own the destination. I find that genuinely moving, and I want to say so clearly, it is one of the better things our species has done, and it was done preemptively, before anyone had arrived anywhere. Now, what the treaty does not settle, because the gaps are where the interesting problems live. The first gap is resources. The treaty forbids appropriating territory. It says considerably less about extracting materials. If a company mines ice from the Martian subsurface and turns it into water and oxygen, has it appropriated anything? Most legal readings say no. On the analogy of fishing in international waters, where nobody owns the sea, but the catch belongs to whoever caught it. That analogy strains at a certain point. If there is exactly one accessible ice deposit within reach of a settlement, and one group is extracting from it continuously, they have not claimed the land in any legal sense, and they have functionally excluded everyone else from the only thing that matters there. Several countries have moved to clarify this on their own. The United States passed legislation in 2015 affirming that American citizens may own resources they extract from space bodies. Luxembourg passed a comparable law in 2017. The Artemis Accords, a set of principles first signed in October of 2020 and joined by a growing number of countries since, address resource extraction and the concept of safety zones around operations. Not everyone agrees with this direction. There have been objections that national laws about space resources sit uneasily with a treaty declaring space the province of all mankind. And Russia has been notably critical of the Accords approach. This is a live international disagreement. And I am reporting it as such rather than picking a side. The second gap is the one this chapter is really about. The treaty is a document about states. It says nothing meaningful about how the people at the destination govern themselves. Article 8 establishes that a state retains jurisdiction over objects it launches and over personnel aboard them. So a habitat is legally an extension of whoever registered it, in roughly the way a ship at sea falls under the law of its flag. That works well enough for a mission of 18 months with 6 people who are employees of an agency, operating under an existing chain of command. It works considerably less well for 100 people, several years in, some of whom work for one organization and some for another. And here I want to introduce the actual problem. Because it is not legal, it is physical. Wearing legal clothing. Let me first say the thing that is often claimed here, and that is not true, because I would rather correct it than repeat it. People often say that every human governance arrangement has always operated with the possibility of leaving. That is simply false as history. Human societies have restricted exit constantly, and sometimes with extraordinary brutality. Enslaved people could not leave. Prisoners cannot leave. Crews on sailing ships in the middle of an ocean could not leave. Which is exactly why maritime law developed such severe provisions around mutiny. Penal colonies existed precisely to make leaving impossible. Besieged cities. closed borders. Systems built specifically around controlling movement. For an enormous number of human beings across history, departure was not available in any meaningful sense. So, the novelty on Mars is not that people would live under an authority they cannot escape. We have done that to each other many times. The novelty is what escape would mean on Earth. In every one of those cases, leaving was forbidden, or dangerous, or impossible to arrange. It was never biologically incoherent. A person who somehow got outside the prison, off the ship, past the border, was in an environment that would keep them alive. The air was still there. The pressure was still there. Water existed somewhere. Escape was an enormous practical problem, and the world on the other side of the wall was still a world. On Mars, the air itself belongs to the settlement. A person who walks out of that habitat is not in a hostile environment. They are in an environment that provides nothing whatsoever. There is no air at any pressure a body can use. There is no water in a form anyone can drink. There is no food and no possibility of any independent biological survival outside the settlement is not difficult. It is physically impossible. At any level of skill or determination. Permanently. Which means every dependency runs through the same institution. The oxygen is produced by machines the settlement owns. Powered by a reactor the settlement owns. In a building, the settlement maintains. Feeding a greenhouse, the settlement tends. There is no second supplier. There is no wilderness to disappear into. There is no next town. I want to be careful here, because it would be easy to slide into a science fiction scenario. And I promised, at the beginning, that I would not invent things. I am not predicting tyranny. I have no idea how those communities would be governed, and neither does anyone else. There are thoughtful people working on space governance who have proposed careful frameworks, and there is no reason to assume the worst. What I am pointing at is a structural fact. Every governance arrangement we have experience of, including the harshest ones, has operated in a world where the physical substrate of life was not owned by anyone. Air has never been a deliverable. We do not know how human institutions behave when it is, because it never has been. That line is blank. Not because we tested it and it failed. Because the situation has never existed. The closest analogues are instructive but incomplete. Ships at sea, submarines, Antarctic stations. Every one of those has an end date measured in months and a home to return to. And every one of them contains only people who signed up. A settlement contains people who were born there. That is the piece with no analogue anywhere. A person born on Mars did not consent to the governance arrangement, cannot leave it, and depends on it for the air in their lungs. The frameworks we have for thinking about legitimacy and consent all evolved in a world where the ground was free and the atmosphere was nobody's property. And now we have finished the survey. Every room has been walked, the road in, and the radiation, and the landing, and the air, and the surface itself, and the buried shelter, and the dust, and the body, and the medicine, and the sealed system, and the dinner table, and the oxygen, and the water, and the isolation, and the children, and the screw, and the law. Some of it is measured. Some of it is debated. A handful of things have never been tested by anyone. But I told you at the beginning that none of these was the terrifying problem. I said it was singular, and that it would only become visible after everything else had been laid out side by side. Everything is laid out now. This is a chapter about an idea, and ideas are gentle company. Nothing here can reach you. Before I name the problem, I owe you something, and it is the most important paragraph in this video. What follows is my own editorial judgment, not a measurement, not a finding. It is a conclusion I have reached from the evidence we walked through. And thoughtful people who know this subject far better than I do disagree with it. So I am going to give you their case first, at full strength, and then answer each part of it as honestly as I can. If you end the night persuaded by them rather than by me, that is a perfectly good outcome, and the survey will still have done its job. Here is the strongest version of the case for Mars settlement, in 3 arguments. The first is about timescale. Almost everyone who dismisses Mars as a backup is thinking in centuries. The serious version of the argument thinks in millions of years. On that scale, the survival of a species confined to one planet is not assured by anything. Large impacts have occurred and will occur again. The sun's output will change. Over deep time, a single point of failure is a single point of failure, however comfortable it currently is. The second is about the nature of failure. A catastrophe that damages Earth might well damage every shelter on Earth at the same time, because they share the same atmosphere, the same climate system, the same supply chains, and the same politics. A settlement 400 million kilometers away shares none of those. Its independence is not a matter of degree. It is structural. That is a real property that no bunker in Antarctica possesses, however well built. The third is about capability rather than insurance. The claim is that the ability to build a genuinely closed, self-sufficient life support system cannot be developed by simulation. Biosphere Two failed, partly because it did not have to succeed. Nobody was going to die. The valve was there, only the actual attempt, with actual stakes and actual isolation, forces the problem to be solved, and a species that had solved it would possess something enormously valuable regardless of where it applied that knowledge, including here. Those are good arguments. Let me answer them. On timescale, I accept this one, and I want to say so plainly, because accepting it is the honest thing to do. Over millions of years, a second location genuinely does reduce risk, in a way nothing on Earth can. I am not going to argue with that. But notice what accepting it costs the argument. The backup claim is almost never deployed on that timescale. It is deployed now, about this century, as a reason to hurry, and on the timescale where it is actually used. It does not work. A defense of Mars that only succeeds across geological time is not a defense of doing it urgently, and urgency is what the sentence is used to justify. On structural independence, this is the strongest of the 3, and I think it is genuinely half right. Independence from shared failure modes is real, and no terrestrial shelter has it. But independence cuts in 2 directions, and the second direction is usually left out. A settlement independent of Earth's failures is also independent of Earth's help. And, for the next several centuries, a Mars settlement would depend on Earth for spare parts, for expertise, for replacement people, and for every industrial product above a certain complexity, which Chapter 17, spent an entire chapter demonstrating a colony that cannot make a screw is not a backup. It is a dependency with a longer supply line. So the structural independence argument is correct about the physics and premature about the timing. It describes a property that a mature, self-sufficient settlement would have, and uses it to justify building an immature one, which would not have it. On capability, this is the argument I find hardest, and I want to give it its due before I disagree, because it uses my own Chapter 11 against me, and it does so fairly. It is true that Biosphere 2 had a valve. It is true that stakes change what people solve. There is a real pattern in engineering history where problems remain unsolved until something forces them. But look at what the argument is actually proposing. It says we should attempt the hardest possible version of closed-loop life support, at the greatest possible distance, with no resupply and no rescue, in order to learn how to do closed-loop life support. That is not how any other difficult technology has ever been developed. We did not learn to build aircraft by first attempting an ocean crossing, and the forcing function the argument wants does not require Mars at all, a sealed facility in Antarctica, or on the sea floor, with a genuine commitment to no resupply for 5 years and real consequences for failure, would apply nearly the same pressure at a fraction of the cost, with the enormous advantage that when something goes wrong, as it did in Arizona, the people inside survive to write the paper. The forcing function is worth having. The distance is not what provides it. So, having said all that, here is what I actually think. The terrifying problem with colonizing Mars is not radiation, or gravity, or dust, or distance, or law. It is a sentence. It gets repeated constantly, by serious people and by enthusiastic people, and by people who have never thought about it for more than a moment. And it most often serves as the reason for the entire enterprise. We need Mars as a backup planet. It appears in interviews, in fundraising material, in documentaries, in classrooms. It comes in several forms. Insurance policy for humanity, not keeping all our eggs in one basket. A second home in case something happens to the first. And after everything we have surveyed tonight, that sentence does not survive contact with its own arithmetic. Not on the timescale where almost everyone actually uses it. Let me be precise about the claim, because the precision is the whole point. For nearly every catastrophe relevant to civilization on human timescales, preserving or rebuilding a habitable environment on Earth would be vastly easier than creating an independent civilization on present-day Mars. Note what that does not say. It does not say Mars is worthless. It does not say no catastrophe could ever change the calculation. It says that on the timescale where the backup argument is actually deployed, meaning the next few centuries, the argument runs backward. Here is why. Consider an asteroid impact of the kind that ended the age of the dinosaurs. That event, 66 million years ago, was as bad as anything the inner solar system routinely produces. It caused a mass extinction and changed the climate for years. And, in the aftermath, large regions of Earth still had atmospheric pressure at around 1,000 millibars, still had accessible liquid water, still had a magnetic field and an ozone layer, still had a gravity every organism was adapted to, and soil with organic material in it, and a biosphere that recovered. It was a catastrophe. It was also, by an enormous margin, more workable for human life than Mars is on its best day. Consider a full nuclear exchange, which generated a good deal of this thinking in the first place. Terrible beyond description. And afterward, large regions of the planet would still retain breathable atmospheric pressure, reachable water, ordinary gravity, and environmental resources that a Mars settlement would have to manufacture from nothing. I am not claiming every location would be safe. Many would not. I am claiming that the recovery problem, however brutal, is a smaller problem than starting a self-sufficient industrial civilization somewhere with 6 millibars of carbon dioxide. Consider severe human-driven climate change at the high end of credible projections. Devastating, displacing, expensive beyond calculation. And a hotter Earth with higher seas is still a place where large regions have air a person can breathe, which describes no square meter of Mars anywhere. Consider a pandemic. Consider a supervolcano. Consider almost any scenario in the standard list. The pattern holds with remarkable consistency. Mars starts below the floor. The worst plausible version of this planet, in the next several centuries, still has air, water, pressure, gravity, and a magnetic field. And Mars has none of those, and will not, without an amount of engineering that dwarfs the catastrophe itself. And here is the structural point underneath all of it. If you can build a sealed, self-sufficient, radiation-shielded habitat that survives indefinitely without resupply, then you can build that same habitat in Antarctica, or on the seafloor, or in the crater of the impact itself, at a tiny fraction of the cost, with breathable air outside the door for emergencies, and with the entire industrial capacity of a planet available for spare parts. The backup argument requires you to solve a harder version of the problem on Mars in order to escape an easier version of the problem here. Now, let me name what actually makes this terrifying. Because a flawed argument alone is not frightening. Wrong arguments are ordinary. What is frightening is what the argument does. It supplies permission. If Mars is a lifeboat, then Earth is a ship that may sink, and a certain kind of thinking follows. It becomes possible to hold, somewhere at the back of the mind, the idea that this planet is a stage we might pass through, that there is a fallback, that the loss of this world would be a tragedy rather than the end of everything we are. There is no fallback on any timescale that matters to anyone alive. That is the finding of tonight's survey, and it took 18 chapters to establish properly. And it is the most important thing I can tell you. This planet is not our first home. For the foreseeable future, it is our only viable one. And the margin is not close. It is not a matter of degree. Every other location available to us in this solar system is lethal in ways that would require permanent industrial intervention to hold at bay. Forever. With no day off. We do not have a spare. We have one, and it makes its own air. Now, the other half of this chapter, because I would be doing exactly what I criticized at the beginning if I stopped here. Demolishing the backup argument does not demolish Mars. It removes one bad reason and leaves the good ones standing. And the good ones are excellent. The first is the biological question, and it is one of the largest questions our species has ever been able to actually approach. Did life arise twice in one solar system? Mars was, by the current evidence, warmer and wetter billions of years ago. There were bodies of standing water. The evidence for ancient habitability is substantial. And the Perseverance rover is currently caching samples in Jezero crater, which appears to have been a river delta, for a possible future return to Earth. If life arose independently twice in one solar system, that would be powerful evidence that life may begin readily wherever conditions permit. It would not by itself tell us how common those conditions are across the galaxy. And there is a genuine complication in that rock has traveled between Earth and Mars for billions of years. So, establishing true independence would itself be difficult work. But it would move one of the oldest questions we have further in one step than anything else could. And if we search thoroughly and find nothing, that constrains some possibilities too, though we should be careful there as well. Absence of detection would not prove that Mars was always lifeless. The evidence may have been destroyed. The search area is minute. The instruments have limits, and the samples have not yet come home. That is a question worth a great deal of money and a great deal of risk. And it does not require anyone to settle anywhere. It requires excellent robots and some carefully chosen human expeditions. The second reason is what Mars preserves. It once had a global magnetic field and lost it. It once had liquid water at the surface and lost most of it. It once had a thicker atmosphere and lost that too. The mechanisms are still being worked out, and NASA's MAVEN mission has spent years measuring how the solar wind strips gas away from an unprotected planet. Mars preserves a record of a rocky world that lost much of its atmosphere and surface water, and it is the only such record within our reach. Understanding it is not an abstract exercise. It is the study of what happens when a planet's protective systems go. And the third reason is the plainest, and I want to state it without embarrassment, because it is there, and because going is what we do. Human beings have crossed oceans in boats that had no business crossing them, and walked into deserts, and stood on ice, and gone into caves, largely for reasons that could not be justified on a spreadsheet. That impulse has produced most of what we value. It does not need a survival justification, and it is weakened by being given a false one. So, here is the conclusion of this survey, and it is not a negative one. Go. Send people. Send them carefully, with the gravity question answered first, and with a serious effort at the reproductive question before anyone talks about permanence. Build the base. Do the science. Bring back the samples. Find out whether we were alone in this solar system. But do it as exploration, which is honest, rather than as escape, which is not. The dream was never wrong. Only one of the reasons was. And once you set that reason down, something happens to the way this planet looks. Let the survey close now. The clipboard can go down. There is nothing left to inspect. I want to spend these last minutes doing something simpler than anything we have done tonight, which is to notice where you already are. Outside the room you are lying in, there is air. It is at around 1013 millibars, and it is roughly 21% oxygen. And it has been sitting there at that pressure and that composition all day without anyone monitoring it. Nobody produced it. There is no plant running. No ceramic cell heated to 800 degrees. No power budget. No maintenance schedule. No technician on call. It is simply there, in unimaginable quantity, given away for free. And it will still be there in the morning, whether or not anyone remembers to check. There is a magnetic field around this room, generated by molten iron moving several thousand kilometers beneath you. It has been deflecting charged particles away from your body every second of your life. It will do so tonight while you sleep. And it has never once required anything from you. Above the roof, there is a column of atmosphere running up to the edge of space. 10,000 kilograms of it standing over every square meter. Stopping the radiation. We spent Chapter 3 measuring. There is an ozone layer in it. There is water vapor moving through it, on its way to falling somewhere as rain. Somewhere within a short walk of where you are lying, there is food. Fruit that grew on a tree with no lighting budget. Grain from a field that was watered by weather, and this room is at 1 g, the full amount. Your skeleton is receiving the exact signal it evolved to expect, and has received it every moment since before you were born. And every question we raised in Chapter 9 is simply answered here. Permanently. By the ground. None of this is a small thing. We spent an entire evening establishing exactly how large a thing it is, by looking carefully at the nearest place that has none of it. Let your body go heavy now. There is one more thing worth noticing, and it is my favorite fact of the whole night. You can go outside. Right now, if you wanted to, you could stand up, walk to a door, open it, and step out with nothing on. No suit, no helmet, no dosimeter, no checklist, no partner watching your oxygen, no running total kept by anyone. There would be no cost recorded anywhere. That is available to you tonight. And it will be available tomorrow. And it has been available every single day of your life. And I would guess you have never once thought of it as a privilege. It is the rarest thing we know of. In the entire surveyed solar system, there is exactly one place where a human being can walk out of a building and simply be alive. And you are lying inside it. Consider what tonight actually was. One last time. We went looking for the terrifying problem with going to Mars. And we found it. And it turned out not to be out there at all. It was here. In a sentence, people repeat about this planet without examining it. The frightening thing was never the radiation, or the dust, or the distance. It was the idea that any of this is replaceable. It is not. And knowing that is not a burden. It is a correction. And corrections make things clearer. So Mars is still there tonight, 400 million kilometers away, or 55 million depending on the month, turning slowly, cold and dry and beautifully strange. And now you know what it is actually like out there, which most people do not. The soft golden sky, the small sun, the sound that dies within a few steps, the blue light spreading out from a setting sun that no human eye has ever watched in person. A rover is sitting in Jezero crater right now, going quietly about its work, with a small golden box inside it that once took a breath of another planet's air and turned some of it into oxygen. It is not waiting for us. It has been doing exactly this for 4.5 billion years, and it will continue whether or not anyone ever arrives. We will go, probably, not tonight, and not soon, and not for the reason most often given, but people will stand there eventually, in that silence, under that sky, and one of them will look up at the end of a long day and find a bright point of light low in the evening, with a smaller point beside it, and they will understand what we have been saying all night better than anyone has ever understood it. Until then, the road opens when the orbits allow it, and the question stays open. and none of it requires anything from you at all. Nothing from tonight needs to stay with you. Not the 6 millibars. Not the names. Not the years. All of it will still be true in the morning without any help from you. Exactly as it has been true for a very long time. Keep only this. If anything, the air outside your window is free, and it is at exactly the right pressure, and it always has been. Your breathing can slow all the way down now. There is nothing left to inspect and nothing left to decide. Good night. Rest easy. Here, on the only place there is,